This is a collection of quiet, mostly useless facts about the brain you are currently using to listen to this. They are not important. They will not change your life. They are simply here to occupy the space between you and sleep. For instance, the brain cannot feel pain. The brain is about 73% water. That means most of what sits inside your skull is not solid tissue, but fluid, a watery matrix that gives it a soft, almost gelatinous consistency. If you were to hold a living brain in your hand, it would feel similar to soft tofu. It has no rigid structure like muscle or bone, just this delicate, moist mass that requires constant hydration to function properly. Despite being only about 2% of total body weight, the brain consumes roughly 20% of the oxygen you breathe. A small organ with a large appetite for fuel, it demands this constant supply of oxygen because it cannot store energy the way muscles can store glycogen. Every breath you take sends a significant portion of that oxygen directly upward to feed the brain's ceaseless activity. The brain has no pain receptors at all. Nociceptors, the nerve endings that detect tissue damage, are absent from brain tissue itself. This is why neurosurgeons can operate on a patient who is awake and feel nothing when they touch the brain. The surrounding membranes and the scalp have plenty of pain receptors, but the organ itself remains silent to touch. Neurons are among the longest living cells in the human body. Many of the neurons you possess today were formed before you were born and will remain with you for your entire life. Unlike skin cells or blood cells that regenerate constantly, most neurons are not replaced. They are a permanent fixture, aging alongside you from infancy to old age. The left hemisphere of the brain controls movement on the right side of the body, and the right hemisphere controls the left side. This crossing over happens in the brainstem, where nerve fibers decussate or cross from one side to the other. The result is a contralateral arrangement, meaning each half of your brain is responsible for the opposite half of your physical experience. The brain's storage capacity is considered virtually unlimited. While early estimates suggested a fixed number of memories, modern neuroscience proposes that the brain can continue forming new connections throughout life. The number of possible synaptic combinations is so astronomically high that you will never reach a point of being full. The brain generates about 20 watts of electrical power when awake. That is roughly the same energy required to power a dim light bulb. This electricity comes from the electrochemical signals that neurons use to communicate with one another, a constant low-voltage buzz of activity that never truly stops, even during deep sleep. The brain cannot multitask in the way people often believe. It does not perform two complex tasks simultaneously, but instead rapidly switches its attention back and forth between them. This switching takes time and mental energy, which is why trying to do two things at once often feels more tiring than doing them separately. The brain begins to shrink slightly in size during a person's late 20s. This is a normal part of aging, a gradual reduction in volume that continues throughout the rest of life. The shrinkage is most noticeable in the prefrontal cortex, the area responsible for complex planning and decision-making, though the rate of loss varies widely between individuals. The average adult brain weighs about 3 pounds. This number is remarkably consistent across most healthy adults, regardless of intelligence or body size. Albert Einstein's brain weighed about the same as the average. Weight alone tells very little about function or capability. The brain contains approximately 86 billion neurons. That is a specific count derived from a method called the isotropic fractionator, which involves dissolving brain tissue and counting cell nuclei. For comparison, the brain of a cat contains about 300 million neurons, and a dog has roughly 500 million. Each neuron can form thousands of connections with other neurons, creating a network of about 100 trillion synapses. This is the wiring diagram of the human brain, a number so large it is difficult to conceptualize. If you were to count all these synapses one per second, it would take you more than 3 million years to finish. The brain produces about 50,000 thoughts per day on average. This estimate comes from studies tracking spontaneous thought patterns, though the exact number is difficult to pin down. Many of these thoughts are repetitive. the same concerns and observations cycling through the mind multiple times over the course of a day. Information travels along neurons at speeds of up to 268 miles per hour. That is faster than a Formula One car. This speed is achieved through a process called saltatory conduction, where electrical signals jump between gaps in the myelin sheath that insulates the nerve fiber. The brain uses about 20% of the body's total energy, despite its small size. This energy is mostly in the form of glucose, which the brain cannot store and must receive continuously through the bloodstream. Even a brief drop in blood sugar can cause noticeable cognitive effects, which is why fasting can feel mentally exhausting. The consistency of the living brain has been compared to gelatin or soft pudding. This softness is why the brain is so vulnerable to injury. It floats within the skull, suspended in cerebrospinal fluid, which acts as a shock absorber, but sudden impacts can still cause the brain to strike the hard bone of the cranium. The brain has no moving parts. Unlike a heart that pumps or lungs that expand, the brain simply processes. It is a static organ in terms of gross movement, yet within it, billions of electrical and chemical events occur every second, all without any visible motion from the outside. The brain's gray matter is actually pinkish gray in living tissue. The gray color only appears after death and preservation. The pinkish hue comes from the high density of blood vessels that supply oxygen and nutrients to the active neurons. The brain contains about 400 miles of blood vessels. This intricate network ensures that every neuron is within a tiny distance of a capillary. If you were to lay out all the blood vessels in the brain, end to end, they would stretch from New York to approximately Cleveland, Ohio. The brain is about 60% fat. This high fat content is essential for the structure of cell membranes and the myelin sheath that speeds up signal transmission. A low-fat diet can actually affect brain function because these fats are not just fuel, but structural components. The brain's optic nerve connects directly from the retina to the visual cortex at the back of the head. This direct connection is why a blow to the back of the head can cause visual disturbances. The optic nerve is actually an extension of the brain itself, not a separate peripheral nerve like those in your arm or leg. The motor cortex, a strip of tissue running from ear to ear, coordinates voluntary movement. Different areas of this strip correspond to different body parts, with the hands and face taking up the most space. This mapping is why fine motor control, such as playing piano or typing, requires so much neural real estate. The sensory cortex sits just behind the motor cortex and processes touch, temperature, and pain from the body. Like the motor cortex, it has a topographic map where each body part has a designated area. The lips and fingertips are overrepresented here, which is why they are so sensitive to touch. The brainstem is responsible for the most basic life support functions: breathing, heart rate, and blood pressure. It sits at the base of the brain like a stalk, connecting the cerebrum to the spinal cord. Damage to this area is often catastrophic because these automatic functions cannot be consciously controlled or relearned. The cerebellum contains more neurons than the rest of the brain combined. This small structure at the back of the head, sometimes called the little brain, holds about 69 billion neurons. Its primary role is coordinating movement and balance, but it also plays a role in attention and language. The hypothalamus, a structure about the size of an almond, regulates body temperature, hunger, thirst, and sleep. It sits at the base of the brain and serves as the body's thermostat and regulatory center. When you feel hot or cold, it is the hypothalamus that initiates the response to correct your temperature. The pituitary gland, which hangs below the hypothalamus, controls growth and other endocrine functions. It releases hormones that trigger other glands to produce their own hormones. This small gland is sometimes called the master gland because its signals cascade throughout the body. The brain regulates heart rate through the autonomic nervous system, which operates without conscious awareness. This system has two branches, sympathetic and parasympathetic, that speed up or slow down the heart as needed. You cannot voluntarily control this in any meaningful way, which is why you cannot simply will your heart to beat faster. The brain controls blinking automatically, with humans blinking about 15 to 20 times per minute. This rate is remarkably consistent across most people. Blinking serves not just to moisten the eye, but also to give the brain a brief moment of visual reset, a tiny interruption that helps process ongoing visual information. The brain receives signals about blood pressure from stretch receptors in the arteries. These sensors send information up to the brainstem, which adjusts heart rate and vessel diameter to maintain stable pressure. This feedback loop operates constantly and never stops, regardless of whether you are asleep or awake. The brain controls the release of melatonin from the pineal gland, a small structure deep in the center of the brain. Melatonin is the hormone that signals when it is time to sleep. Its production increases in darkness and decreases in light, which is why exposure to light in the evening can delay sleep onset. The brain's hippocampus plays a central role in spatial navigation, containing specialized place cells that fire when you are in a specific location. These cells create an internal map of your environment. When you move through a familiar space, these neurons fire in sequence, tracking your progress through the environment. The brain's prefrontal cortex is not fully developed until the mid-20s. This area handles complex decision-making, impulse control, and long-term planning. The late maturation of this region explains why teenagers and young adults often make decisions that seem short-sighted to older individuals. The brain has a built-in filter that prevents it from being overwhelmed by sensory input. The reticular activating system sits at the top of the brainstem and acts as a gatekeeper, filtering out background sounds and sights so you can focus on what is important. This is why you can sleep through a distant train but wake up when someone says your name. The brain of a newborn is about 1/4 the size of an adult brain, but contains almost the same number of neurons. The growth in size comes from the formation of connections between those neurons, not the production of new ones. This connectivity explosion in early childhood is what drives the rapid learning and development of the first few years of life. The brain's left hemisphere tends to specialize in language processing for most people. This lateralization is present from early childhood and becomes more pronounced with age. About 95% of right-handed people have language centers in the left hemisphere, while the majority of left-handed people do as well. The brain's ability to recover from injury is called neuroplasticity. This is not a fixed capacity, but varies widely depending on age and the nature of the injury. Young brains are more plastic, which is why children can recover from strokes that would leave an adult permanently disabled. The brain can process the concept of zero, an ability that is surprisingly rare in the animal kingdom. Recognizing zero as a quantity rather than just absence requires abstract thinking. Some birds and primates have shown this ability, but the human brain develops it relatively early in childhood. The brain's default mode network is active when you are not focused on an external task. This network involves several brain regions that communicate during daydreaming and self-reflection. When your mind wanders, it is not idle, but engaging in a specific type of internal processing that some researchers believe is essential for creativity. Short-term memory lasts only about 20 to 30 seconds. This is the brief holding tank, where information sits before it, either fades away or moves into longer storage. If you are not actively rehearsing a phone number or a name during those 30 seconds, it will simply evaporate from your awareness, gone as if it was never there at all. The brain can recognize a familiar image in as little as 13 milliseconds. That is roughly 1/10 of the time it takes to blink. This rapid processing happens without conscious effort, a split-second identification that occurs before you have even registered that you have seen anything at all. Memories are not stored in one single location. They are distributed across the cortex, with different aspects of a memory kept in different regions. The visual details are held in one area, the sounds in another, the emotions in yet another, all stitched together by the hippocampus into a unified experience. The brain tends to remember unfinished tasks better than completed ones. This is known as the Zeigarnik effect, named after the psychologist who first observed it in the 1920s. The brain holds on to incomplete actions in a state of readiness, as though it is waiting for closure, which is why cliffhangers and unresolved stories linger so stubbornly in your mind. High levels of stress can actually shrink the volume of the hippocampus. Cortisol, the primary stress hormone, damages neurons in this memory formation region when it remains elevated for too long. This is one reason why chronic stress can make it harder to learn new things or recall recent events. The brain fills in blind spots in our vision without us ever noticing. Each eye has a small area where the optic nerve exits the retina, leaving it with no light-detecting cells. The brain simply takes visual information from surrounding areas and seamlessly paints over the gap, creating an illusion of complete visual coverage. Earworms, those repetitive songs that get stuck in your head, tend to be simple in structure. They often have a repetitive rhythm and a predictable melodic contour. The brain's tendency to latch onto these patterns is related to the way it processes and expects sequences, making certain tunes virtually impossible to ignore. The brain processes visual information faster than auditory information. A visual stimulus can be detected and identified in about 100 milliseconds, while sound typically takes longer. This difference is why watching someone speak can sometimes help you understand them better, as the visual cues arrive slightly ahead of the auditory ones. Dehydration, by as little as 2% of body weight, can impair cognitive performance. Even mild water loss can affect concentration, alertness, and short-term memory. This is not a dramatic effect but a subtle dulling, a slight slowing of processing speed that you might not even notice, but that measurably affects how well the brain functions. Reading aloud uses different neural pathways than reading silently. Silent reading primarily engages the visual cortex and language areas, while reading aloud adds motor planning and auditory feedback. These pathways can actually interfere with each other, which is why reading aloud often feels slower and more effortful. The brain often confuses similar memories, leading to false recollections. This happens because memories are not stored as perfect recordings, but as reconstructions assembled from various pieces of information. When two memories share similar features, the brain can accidentally merge them, producing a recollection that feels real, but is not entirely accurate. It takes about 66 days to form a habit on average. This number comes from a study that tracked participants as they learned a new behavior, such as daily flossing or drinking more water. Some habits formed in as little as 18 days, while others took more than 200, but 66 days represents the statistical middle point of this process. The brain's working memory can hold about 4 distinct items at a time. This is a more recent estimate that has largely replaced the older figure of 7 plus or minus 2. The exact number depends on the complexity of the items, but regardless, your conscious workspace is surprisingly small. The brain can remember an estimated 1 quadrillion individual pieces of information over a lifetime. This figure comes from calculations based on the number of synapses and their potential storage capacity. You will never reach a point where your brain is too full to learn something new. The brain processes emotional memories more deeply than neutral ones. Events that are tied to strong emotions, whether positive or negative, are more likely to be remembered clearly and for longer periods. The amygdala, a structure deep in the brain, tags these memories with an emotional marker that prioritizes them for storage. The brain experiences sensory adaptation where it stops noticing constant, unchanging stimuli. This is why you do not feel your clothes on your skin after a few minutes of wearing them. The brain filters out information that is predictable and unchanging, saving its processing power for novel or significant events. The brain's hippocampus is essential for forming new memories, but not for storing them long-term. Once a memory has been consolidated, it becomes independent of the hippocampus and is stored elsewhere in the cortex. This is why people with hippocampal damage can remember events from their childhood, but cannot form new memories. The brain can process the meaning of a word in under 200 milliseconds. This rapid comprehension happens automatically every time you read or hear language. The entire sequence from word recognition to full understanding occurs faster than most people realize. The brain's ability to recognize faces is highly specialized. A specific region called the fusiform face area responds almost exclusively to facial stimuli. This processing is so refined that humans can identify thousands of different faces, distinguishing subtle differences in spacing and proportion with remarkable accuracy. The brain can be tricked by optical illusions because it makes assumptions about the visual world. These assumptions are usually correct, but are occasionally wrong, leading to perceptions that do not match reality. The brain prefers to impose order and predictability on ambiguous visual information. The brain's perception of time changes under different emotional states. Time seems to pass more quickly when you are engaged in enjoyable activities, and more slowly when you are bored or anxious. This temporal distortion is a reflection of how the brain processes and stores memories of events. The brain has a separate system for recognizing objects versus faces. Damage to one system does not necessarily affect the other. A person can lose the ability to recognize faces, a condition called prosopagnosia, while still identifying objects perfectly well. The brain processes color before it processes shape. The visual system handles these features in parallel but slightly different timelines. This separation of processing is why you can sometimes identify that something is green before you understand what it is. The brain's memory retrieval is influenced by context. If you learn information in a particular environment, you are more likely to recall that information when you are in the same environment again. This context-dependent memory is one reason why studying in the same room where you will take a test can be beneficial. The brain can recognize a song after hearing only a few notes. This rapid identification is based on pattern recognition, the same system that helps you recognize faces and voices. The brain is constantly scanning incoming sensory information for familiar patterns. The brain's ability to focus on a single conversation in a noisy room is called the cocktail party effect. This selective attention allows you to filter out background noise while still being able to hear your name if it is mentioned. The brain is constantly monitoring the unattended channels for personally relevant information. The brain processes pain signals through multiple pathways, including one that carries fast, sharp pain and another that handles slower, duller pain. These pathways are independent and can be activated separately. This is why a burn can produce immediate, sharp pain followed by a longer-lasting ache. The brain's hypothalamus plays a role in regulating thirst, hunger, and sleep. This small region is constantly monitoring your body's internal state and initiating appropriate responses. When you are dehydrated, the hypothalamus triggers the sensation of thirst, which motivates you to drink. The brain can experience phantom limb sensations after an amputation. The brain's map of the body still includes the missing limb, and signals from other parts of the body can be interpreted as coming from the absent area. This phenomenon demonstrates how much of perception is constructed by the brain rather than directly determined by sensory input. The brain processes sensory information from the left side of the body in the right hemisphere, and vice versa. This contralateral organization applies to sight, sound, and touch, making the brain a cross-wired organ. This arrangement occurs because nerve pathways decussate or cross over at various points in the central nervous system. The brain's motor system can compensate for physical changes in the body. If a muscle is weakened, the brain can recruit other muscles to perform the same movement, albeit less efficiently. This adaptability is one reason why people can often continue functioning after relatively minor injuries. The brain has separate systems for recognizing faces and for interpreting facial expressions. You can recognize a person's face without understanding their emotional state, and vice versa. This dissociation is evidence of the brain's modular organization, with different tasks distributed to specialized regions. The brain's auditory system can localize sounds to within a few degrees of accuracy. This is achieved by comparing the tiny differences in time and intensity between the sound arriving at each ear. The brain calculates these differences almost instantaneously, allowing you to turn toward a sudden noise without consciously thinking about it. The brain's olfactory system is the only sensory system that bypasses the thalamus. Scents are processed directly by the olfactory bulb, which sends information to the amygdala and hippocampus. This direct connection is why smells can trigger such vivid and immediate emotional memories. The brain's ability to recognize language is specialized for sounds, but it also processes written words through the same language network. This is possible because the brain learns to map visual symbols to auditory representations, a skill that must be acquired through education. The word brain comes from Old English brain, which is related to similar words in other Germanic languages. This root has been used for over 1,000 years to describe the organ inside the skull. The word itself has remained remarkably stable, changing very little over centuries of use. The study of language structure is called morphology, a branch of linguistics that examines how words are formed. Morphologists look at the smallest units of meaning, called morphemes, and how they combine to create words. This is different from phonology, which studies sounds, and syntax, which studies sentence structure. The word mind is actually unrelated to the word mine, despite their similar spelling. Mind comes from the Old English gemind, meaning memory or thought, while mine comes from the Old English min, a possessive pronoun. These two words look alike in modern English, but have entirely separate histories. The longest word in English is the chemical name for the protein titin, which has 189,819 letters. This word is so long that it takes over 3 hours to pronounce in its entirety. The full name describes the complete sequence of amino acids in the protein, making it essentially a chemical formula written as a word. The word set holds the record for the most dictionary definitions, with over 400 distinct meanings. This single 3-letter word can be a verb, noun, or adjective, covering everything from placing an object down to establishing a rule to a collection of things. Its versatility makes it one of the most frequently used words in English. Uncopyrightable is one of the longest common words in English that does not repeat any letter. It contains 15 distinct letters. Another word with this property is dermatoglyphics, which refers to the study of fingerprints and also uses 15 unrepeated letters. The word goodbye originated as a contraction of a phrase that originally meant God be with you. Over time, the phrase was shortened and altered through common usage until it became the single word we use today. The secular version has lost its original religious meaning and is now simply a standard farewell. Bookkeeper is one of the few English words with 3 consecutive sets of double letters. It has the double O, the double K, and the double E all in a row. This unusual spelling pattern makes it a favorite among word enthusiasts and spelling bee participants. The word Q is pronounced exactly the same whether you pronounce all 5 letters or just the first one. The remaining 4 letters, U, E, U, E, are completely silent. This word came into English from French, where it originally meant tail, and it has retained its unusual spelling despite its simple pronunciation. Eunoia is the shortest English word that contains all 5 main vowels. It has only 6 letters total. The word means beautiful thinking or a well-balanced mind, and it comes from Greek roots, making it both a linguistic curiosity and a fitting term for a channel about the mind. The word pneumonultra microscopic silicovolcanoconiosis was artificially coined to be the longest word in English. It describes a lung disease caused by inhaling very fine silica dust. Despite its impressive length, it was intentionally created for the purpose of being a long word. The letter E is the most frequently used letter in the English language. It appears in about 12.7% of all written English text. This is followed by A and then R, with the letter Z appearing least frequently at only about 1%. The word oxymoron is itself an oxymoron, a term for a contradiction in terms. It comes from the Greek words for sharp and dull, combined into a single word. This self-referential quality makes it a favorite among linguists and word enthusiasts. The word book comes from the Germanic word for beech tree. This is because early Germanic peoples used beechwood tablets for writing. Over time, the material gave its name to the object itself, a common pattern in language history. The word barbarian originally meant anyone who did not speak Greek. To the ancient Greeks, foreign speech sounded like barbar, a kind of unintelligible babbling. The word eventually evolved to mean someone uncivilized or uncultured. The word hypocrite originally meant actor in ancient Greek. The root hypocrites referred to someone who wore a mask and performed on stage. Over time, the meaning shifted to someone who pretends to be something they are not, losing its theatrical association entirely. The word sarcasm comes from the Greek word sarkazine, which means to tear flesh. This violent origin reflects the sharp, cutting nature of sarcastic remarks. The word itself carries the sense of a verbal wound, a linguistic bite that can leave a mark. The word tragedy means goat song in Greek, a reference to the satyr plays that featured goat-like performers. The connection between goats and tragic theater is not entirely clear, but the word has persisted for over 2,000 years. Today, it retains none of its original goat-related associations. The word clue comes from the Old English clue, meaning a ball of thread. This is a reference to the myth of Theseus, who used a ball of thread to navigate the labyrinth. The word evolved to mean anything that helps solve a puzzle, losing its literal thread connection. The word muscle means little mouse in Latin. This is because early anatomists thought the contracting bicep looked like a small mouse moving under the skin. The word musculus was adopted into English and has retained its animal association in a purely anatomical sense. The word salary comes from the Latin word for salt, salarium. This is because Roman soldiers were sometimes paid in salt or given a salt allowance. The connection has been debated by historians, but the etymology remains a standard piece of linguistic trivia. The word emotion comes from the Latin emovere, meaning to move out. This root captures the sense of being moved by a feeling. The word evolved through French before entering English, retaining its core meaning of an inner movement. The word person comes from the Latin persona, which originally meant a theatrical mask. Actors in Roman theater wore masks that indicated their character, and the word came to mean the character itself. Over time, it shifted from a mask to the individual wearing it. The word trivia itself means crossroads in Latin. The root trivium referred to a place where three roads met, a place where gossip was exchanged. From this origin, the word came to mean unimportant information or idle talk. The word sincere may come from the Latin sincerus, meaning clean or pure. There is a common myth that it comes from sincera, meaning without wax, referring to dishonest merchants hiding flaws in pottery. This explanation is widely repeated, but has no historical basis. The word salary and sauce both come from the same Latin root for salt, sal. Salt was a valuable commodity in ancient times, and words for payment and seasoning both trace back to it. This connection shows how economic and culinary language overlap. The word luxury comes from the Latin luxuria, meaning excess or extravagance. Its original sense was negative, associated with moral weakness. Over time, it shifted to a neutral or even positive meaning. The word disaster comes from the Latin dis and astrum, meaning bad star. The ancient belief was that calamities were caused by unfavorable astrological alignments. The word retains this sense of misfortune, but has lost its connection to the stars in modern usage. The word candidate comes from the Latin candidatus, meaning dressed in white. In ancient Rome, those seeking office wore white togas to symbolize their purity and integrity. The connection to clothing is now lost, but the word remains a standard term for someone seeking election. The word genius comes from the Latin genius, meaning a guardian spirit. In ancient Rome, each person was believed to have a tutelary spirit that guided them. The word evolved to mean exceptional intellectual ability, leaving its spiritual origins behind. The word nice once meant foolish or stupid in Old French. It gradually shifted through various meanings to become the positive term we use today. This semantic drift is common in language, where words can change meaning entirely over centuries. The word silly originally meant blessed or happy. It then shifted to mean innocent, then naive, and eventually foolish or ridiculous. This progression shows how language evolves through layers of meaning over time. The word nice and silly both demonstrate how words can drift from their original meanings. Language is constantly shifting, with words gaining and losing associations over time. What a word means today is often quite different from what it meant centuries ago. The study of sleep is called somnology, a field that examines the physiological and neurological processes of sleep. Somnologists investigate everything from brainwave patterns to the effects of sleep deprivation. This is a relatively young science, with most major discoveries occurring in the last century. Circadian rhythms, the internal biological clocks that regulate sleep-wake cycles, actually run slightly longer than 24 hours without external cues. In the absence of natural light or time cues, these rhythms settle at about 24.2 hours. This is why humans naturally tend to drift toward later bedtimes when left without schedules. Most dreaming occurs during REM sleep, which stands for rapid eye movement. This stage is characterized by quick, darting eye movements and a brain that is almost as active as when awake. REM sleep typically begins about 90 minutes after falling asleep and recurs throughout the night in cycles. The body is temporarily paralyzed during REM sleep to prevent acting out dreams. This paralysis is called atonia, and it affects all voluntary muscles except those needed for breathing and eye movement. This mechanism is essential for safety, as it prevents the physical enactment of dream content. Humans spend roughly 1/3 of their lives sleeping. This means an average person will sleep for about 25 years over a typical lifetime. This significant portion of life is not wasted time, but essential maintenance and consolidation. The brain is actually more active during REM sleep than when fully awake. This paradoxical activity is one of the defining features of the REM state. The brain is processing information, consolidating memories, and generating dreams, all while the body remains still and relaxed. The record for the longest period without sleep is about 11 days, set in a 1964 experiment. The subject, a teenager named Randy Gardner, remained awake for that duration under medical supervision. He experienced significant cognitive impairment, but recovered without permanent damage. Sleep helps the brain clear metabolic waste through a system called the glymphatic pathway. This system becomes more active during sleep, flushing out toxic byproducts that accumulate during wakefulness. This waste clearance is essential for long-term brain health and function. People often forget 50% of a dream within 5 minutes of waking. This rapid forgetting happens because dreams are not consolidated into long-term memory. The brain does not prioritize dream content, allowing it to fade quickly unless actively rehearsed or recorded. The body temperature drops slightly before sleep onset, signaling to the brain that it is time to rest. This cooling helps initiate sleep and maintain it throughout the night. Taking a warm bath before bed can actually help lower core temperature, making it easier to fall asleep. Dreaming can occur during non-REM sleep, but these dreams tend to be less vivid and less story-like. Non-REM dreams are often described as more thought-like or fragmentary. The most intense, narrative dreams occur during REM sleep. Sleep needs vary significantly by age, with adults typically requiring 7 to 9 hours per night. Children and teenagers need more, while older adults may need slightly less. The exact amount depends on individual genetics and lifestyle factors. The pineal gland produces melatonin in response to darkness, signaling the onset of sleep. Melatonin levels rise in the evening and fall in the morning. This hormone is not a sleep inducer, but a time cue that helps regulate the sleep-wake cycle. The suprachiasmatic nucleus, located in the hypothalamus, acts as the brain's master clock. This tiny cluster of neurons receives light information from the eyes and synchronizes the body's rhythms. Its activity is essential for maintaining a consistent sleep schedule. Sleep deprivation impairs the brain's ability to form new memories. The hippocampus, which is involved in memory consolidation, becomes less active without adequate sleep. This is why studying for exams is less effective if you sacrifice sleep. The brain consolidates memories during sleep, transferring them from short-term to long-term storage. This process occurs primarily during non-REM sleep. The brain replays the day's events, strengthening the neural connections that encode new information. Sleep spindles are brief bursts of brain activity that occur during stage 2 sleep. These electrical oscillations are associated with memory consolidation. People who produce more sleep spindles tend to have better retention of learned material. The brain cycles through different sleep stages about 4 to 5 times per night. Each cycle lasts about 90 minutes and includes both non-REM and REM sleep. The proportion of REM sleep increases as the night progresses. Night terrors occur during non-REM sleep and are different from nightmares. The sleeper may scream or thrash but does not remember the event upon waking. These episodes are most common in children and usually resolve with age. Sleepwalking also occurs during non-REM sleep, typically in the first few hours after falling asleep. The sleepwalker may appear awake but is actually in a deep sleep state. This behavior is generally harmless and often ceases in adulthood. The brain's default mode network is active during sleep, but its activity changes across sleep stages. This network, which is active during waking daydreaming, also plays a role in sleep processes. Its function during sleep is not fully understood. The brain temperature decreases during sleep, reflecting reduced metabolic activity. This cooling is part of the body's natural rest and recovery cycle. The drop in temperature is one of the physiological markers of sleep onset. Dreams can incorporate external sensory information, such as sounds or smells, into their content. This is why an alarm clock can become part of a dream before waking. The brain continues to process some sensory input even during sleep. The brain's sleep-wake cycle is influenced by adenosine, a chemical that builds up during waking hours. Adenosine promotes sleepiness by inhibiting wake-promoting brain regions. Caffeine works by blocking adenosine receptors, delaying the onset of sleepiness. Sleep quality is as important as sleep quantity, with fragmented sleep reducing its restorative effects. Even if you spend 8 hours in bed, frequent awakenings can prevent deep sleep. Sleep consolidation, or staying asleep throughout the night, is essential for feeling rested. The brain processes emotional information during REM sleep, helping to regulate mood. This is why a good night's sleep can improve emotional resilience. Sleep deprivation often leads to increased irritability and decreased ability to regulate emotions. The brain's glymphatic system is most active during deep sleep, clearing out beta-amyloid proteins. These proteins are associated with Alzheimer's disease. This clearance mechanism is one reason why sleep is so essential for long-term brain health. Dreams are often nonsensical because the prefrontal cortex, which handles logic and planning, is less active during REM sleep. The brain creates narratives without the usual constraints of logic. This is why dreams can seem so strange and disconnected. Lucid dreaming occurs when the sleeper becomes aware that they are dreaming. This awareness can sometimes allow the dreamer to control the dream's content. Lucid dreaming is rare, but can be cultivated with practice. The brain's response to sleep deprivation includes increased activity in the amygdala, which processes emotions. This increased activity makes sleep-deprived individuals more reactive to negative stimuli. Lack of sleep literally changes how the brain processes emotional information. Sleep restores the brain's ability to focus attention, clearing out the neural clutter that accumulates during wakefulness. Without adequate sleep, attention becomes fragmented and inefficient. A rested brain is simply better at maintaining focus on a single task. The brain's sleep needs are partly determined by genetics, with some people being naturally short sleepers. These individuals function well on as little as 4 to 5 hours of sleep. This variation is rare but demonstrates the range of normal sleep needs. The timing of sleep is regulated by both circadian rhythms and the homeostatic drive, or the pressure to sleep that builds up during waking hours. These two systems interact to determine when you feel sleepy and when you naturally wake. Disruptions to either system can interfere with sleep quality. The brain produces delta waves during deep sleep, indicating a state of slow wave activity. These waves are associated with the most restorative sleep. The brain is not inactive during this time, but is engaged in essential recovery processes. Sleep before learning is as important as sleep after learning. A well-rested brain is better at acquiring new information, while sleep after learning helps consolidate it. Both phases are essential for effective memory formation. The brain's ability to regulate body temperature is diminished during REM sleep. This is why the body loses its ability to shiver or sweat during this stage. The brain prioritizes sleep processes over thermoregulation during REM. Sleep allows the brain to prune unnecessary connections, a process called synaptic pruning. This pruning helps maintain efficient neural networks. Without sleep, the brain accumulates too many connections, which can slow processing speed. The brain's response to light is mediated by melanopsin, a photopigment found in the eye. This pigment detects blue light, signaling the brain to suppress melatonin production. This is why exposure to screens before bed can delay sleep onset. The brain can process some information during sleep, such as familiar sounds or even simple words. This processing occurs without conscious awareness. The brain is never entirely offline, even during the deepest stages of sleep. The brain contains approximately 86 billion neurons, a number that was established using a method called the isotropic fractionator. This technique involves dissolving brain tissue and counting cell nuclei, providing a precise count that replaced earlier estimates. For perspective, the brain of a cat has about 300 million neurons, while a dog has roughly 500 million. There are about 100 trillion synaptic connections in the brain, forming an intricate web of communication between neurons. This number is so vast that it is difficult to conceptualize in everyday terms. If you were to count one synapse per second, it would take you more than 3 million years to finish the count. The brain produces about 50,000 thoughts per day on average, according to studies tracking spontaneous thought patterns. This number varies widely between individuals, with some people reporting far more and others far fewer. Many of these thoughts are repetitive, cycling through similar themes and concerns throughout the day. Information travels along neurons at speeds of up to 268 miles per hour, achieved through a process called saltatory conduction. This process involves electrical signals jumping between gaps in the myelin sheath that insulates nerve fibers. The speed ensures rapid communication between different brain regions and the rest of the body. The average attention span has been estimated at around 8 seconds in some studies, though this number is often misrepresented. The original study that produced this figure was conducted on goldfish, not humans. Human attention can be sustained for much longer periods when engaged with meaningful content. The heart beats about 100,000 times per day, a rhythmic process controlled by the brain's autonomic nervous system. This consistent beating is essential for supplying the brain with oxygen and nutrients. Over a lifetime, the heart will beat more than 2.5 billion times. The speed of a sneeze is roughly 100 miles per hour, propelling droplets at high velocity. The brain coordinates this reflex through a complex series of neural signals. The purpose of a sneeze is to clear the nasal passages of irritants. Human reaction time averages around 250 milliseconds, the time it takes to respond to a simple stimulus. This speed varies depending on age, fatigue, and the complexity of the stimulus. Professional athletes often have reaction times significantly faster than the average. The brain consumes about 20 watts of electrical power, enough to power a dim light bulb. This low power consumption is remarkable, given the complexity of the brain's processing. The brain is more energy efficient than any computer currently in existence. The average person walks the equivalent of about 3 times around the world over a lifetime. This calculation is based on an average walking distance of about 75,000 miles over a lifetime. The brain coordinates this movement through continuous feedback from the motor system and sensory input. The human eye can distinguish about 10 million different colors, a remarkable feat of visual processing. This ability comes from 3 types of color receptors in the retina, each sensitive to different wavelengths. The brain integrates these signals to produce the perception of color. The time it takes for a thought to form is measurable in milliseconds, with simple thoughts occurring in under 100 milliseconds. Complex thoughts require more time, involving multiple brain regions. The speed of thought depends on the nature of the information being processed. The brain has about 170,000 miles of blood vessels, a network that ensures every neuron receives adequate oxygen and nutrients. This is longer than the circumference of the Earth. The brain's vascular system is essential for maintaining its high metabolic demands. The brain's weight is about 3 pounds, or approximately 2% of total body weight. Despite its small size, the brain uses about 20% of the body's energy. This disproportionate energy consumption reflects the brain's constant activity. The average adult human brain contains about 100 billion glial cells, which support and protect neurons. Glial cells outnumber neurons by about 10 to 1. These cells are essential for maintaining the brain's structure and function. The brain has about 400 miles of blood vessels, a dense network that supplies oxygen and nutrients. This vascular system is essential for brain function, as the brain cannot store energy. Even brief interruptions in blood flow can cause significant damage. The brain processes about 70,000 thoughts per day in some estimates, though this number is difficult to measure precisely. The brain is constantly active, even when you are not consciously aware of it. This continuous activity is essential for maintaining cognitive function. The brain's memory capacity is estimated at about 2.5 petabytes, according to some researchers. This is roughly equivalent to 3 million hours of television. The exact capacity is difficult to measure, but the brain's storage capabilities are vast. The brain contains about 100 trillion neural connections, more than the number of stars in the Milky Way galaxy. This comparison highlights the brain's extraordinary complexity. The brain is the most complex known structure in the universe. The brain's processing speed is estimated at about 100 trillion operations per second. This speed is achieved through parallel processing, with many neurons working simultaneously. The brain is far more efficient than any current supercomputer. The brain uses about 1/5 of the body's oxygen, despite being only a small fraction of total weight. This high oxygen consumption is necessary for the brain's constant activity. The brain is sensitive to oxygen levels, and even brief hypoxia can cause damage. The brain's electrical activity can be measured in microvolts, with brain waves ranging from less than 1 microvolt to over 100 microvolts. This small voltage is amplified by the scalp and skull. EEG recordings capture this activity through electrodes placed on the scalp. The brain's resting state uses about 20 watts of power, a small amount compared to other organs. The brain's efficiency is remarkable, processing vast amounts of information with minimal energy. This efficiency is one reason why the brain is so difficult to replicate artificially. The brain has about 30 billion neurons in the cerebellum alone, more than the entire brain of many other animals. This structure is responsible for coordinating movement and balance. The cerebellum contains more than half of the brain's total neurons. The brain's hypothalamus contains about 3 million neurons, a small number compared to other regions. Despite its size, the hypothalamus regulates essential functions like temperature and hunger. This small region has a large impact on overall body function. The brain's hippocampus contains about 2 million neurons, a relatively small number for such an important structure. The hippocampus is essential for memory formation and spatial navigation. Damage to this region can cause significant memory impairment. The brain's brainstem contains about 1 million neurons, a small but essential population. These neurons control breathing, heart rate, and blood pressure. The brainstem is one of the oldest parts of the brain in evolutionary terms. The brain's prefrontal cortex contains about 300 million neurons, a large number for such a specialized region. This area is responsible for complex decision-making and impulse control. The prefrontal cortex is one of the most recently evolved parts of the brain. The brain's visual cortex contains about 200 million neurons, a significant portion of the brain's total. This region processes visual information from the eyes. The visual cortex is one of the most studied areas of the brain. The brain's motor cortex contains about 150 million neurons, a smaller number than the visual cortex. This region coordinates voluntary movement. The motor cortex is essential for interacting with the environment. The brain's limbic system contains about 100 million neurons, a relatively small number for such an important system. The limbic system is responsible for emotions and motivation. This system is essential for survival and social interaction. The brain's olfactory bulb contains about 50 million neurons, a small but essential population. This region processes smells and is directly connected to memory centers. The olfactory bulb is one of the few brain regions that can regenerate. The brain's reward system contains about 100,000 neurons, a small but powerful population. These neurons release dopamine, a neurotransmitter associated with pleasure and motivation. The reward system is essential for learning and survival. The brain's brainwaves range from 1 to 40 Hz, depending on the state of consciousness. Delta waves, at 1 to 4 Hz, are associated with deep sleep. Gamma waves, at about 40 Hz, are associated with active processing. The brain's electrical activity is synchronized in some states and desynchronized in others. This synchronization is essential for communication between brain regions. Sleep and wakefulness are associated with different patterns of synchronization. The brain's response to a stimulus occurs within about 100 milliseconds for simple stimuli. This rapid response is essential for survival. The brain must process information quickly to respond to environmental threats. The brain's processing speed slows with age, a natural part of aging. This slowdown is gradual and affects different cognitive domains differently. The brain compensates for this slowdown through other mechanisms. The brain's ability to process information is influenced by many factors, including genetics and environment. Individual differences in processing speed are normal. These differences are not necessarily related to intelligence. The brain's clocks are set by light, regulating the sleep-wake cycle. This entrainment is essential for maintaining a consistent sleep schedule. The brain's internal clock is slightly longer than 24 hours. The brain's time perception is influenced by emotions and attention, with time seeming to pass more slowly when you are bored. This subjective experience reflects the brain's processing of temporal information. The brain's representation of time is not constant, but depends on context. The brain's ability to measure time is not mediated by a single clock, but by multiple neural systems. These systems include the basal ganglia and the cerebellum. The brain processes time intervals of different durations through different mechanisms. The brain's representation of time is essential for coordinating movement and understanding sequences. This temporal processing is fundamental to everyday life. Without it, you could not anticipate when to step off a curb or catch a ball. Phrenology, the study of skull shape as an indicator of personality and mental ability, was a pseudoscience that flourished in the early 1800s. Practitioners claimed that different mental faculties were localized in specific brain regions and that the size of these regions could be determined by feeling bumps on the skull. The practice was eventually discredited as scientific understanding of the brain improved, but it did contribute to the idea that different brain functions might be localized in specific areas. The first blood transfusion in humans was performed in the 17th century using animal blood, a procedure that was almost always fatal. Early physicians believed that animal blood could cure various ailments. The successful transfusion of human blood did not occur until the early 19th century, after the discovery of blood types. The existence of neurons as distinct cells was not established until the late 19th century, largely through the work of Santiago Ramón y Cajal. Using a staining technique developed by Camillo Golgi, Cajal was able to visualize individual nerve cells and their intricate branching patterns. This discovery fundamentally changed the understanding of the nervous system as a network of discrete cells rather than a continuous web. The electroencephalogram, or EEG, was first used to record human brain activity in the 1920s by Hans Berger. Berger was a German psychiatrist who was fascinated by the possibility of measuring the brain's electrical activity. His initial recordings were primitive by modern standards, but they laid the foundation for all subsequent brainwave research. An early theory of memory proposed that memories were stored in the ventricles, the fluid-filled cavities of the brain. This idea persisted for centuries, largely due to the influence of Galen, an ancient Greek physician. It was only with the development of modern neuroscience that the ventricles were recognized as simply fluid spaces, not memory storage sites. The concept of left brain and right brain dominance is largely oversimplified, despite its popularity in popular culture. While it is true that certain functions are lateralized, most cognitive processes involve both hemispheres working together. The popular notion that people are either left-brained or right-brained is not supported by scientific evidence. The word psychology comes from the Greek words psyche, meaning soul, and logia, meaning study. The root psyche originally referred to the breath of life or spirit. In modern usage, psychology is defined as the scientific study of mind and behavior. Early surgical procedures on the brain, known as trepanation, date back thousands of years and were practiced in many ancient cultures. These procedures involved drilling or scraping holes in the skull to release pressure or evil spirits. Some of these individuals survived the surgery, as evidenced by healed bone growth around the holes. The fight-or-flight response was first described by Walter Bradford Cannon in 1915. Cannon, an American physiologist, observed that animals respond to threats by either preparing to fight or flee. This response is mediated by the sympathetic nervous system and involves the release of adrenaline. The first scientific study of memory was conducted by Hermann Ebbinghaus in the 1880s. Ebbinghaus, a German psychologist, used himself as a test subject, memorizing nonsense syllables and measuring how long he retained them. His work established many of the fundamental principles of memory research that are still used today. The brain was once thought to cool the blood, a theory that dates back to ancient Greece. This theory persisted for centuries, largely because it fit with the dominant humor-based understanding of the body. It was only with the development of modern anatomy that the brain was recognized as a processing organ. The concept of neuroplasticity, the idea that the brain can change and reorganize itself, is relatively recent. While the possibility of brain change was suggested by some early researchers, it was not widely accepted until the 1960s and 70s. This understanding has had a profound impact on rehabilitation and treatment of brain injury. The first brain bank, a facility that collects and stores brain tissue for research, was established in the 1950s. The first such facility was at the University of California, Los Angeles. Brain banks are essential for research into neurological diseases. The first successful brain transplant was performed on a dog in the 1950s by Russian surgeon Vladimir Demikov. Demikov transplanted a second head onto a dog, creating a two-headed canine. The dog survived for several days, but the procedure was not considered a true transplant of the brain. The longest study on memory is the Harvard Grant Study, which began in 1938 and is still ongoing. The study followed a group of men for decades, tracking their physical and mental health. The study has provided valuable insights into the factors that contribute to healthy aging. The first fMRI scan of the brain was performed in the 1990s using a technique that measures blood flow changes related to neural activity. This technology allowed researchers to see which areas of the brain were active during different tasks. fMRI has become a standard tool in neuroscience research. The first person to win a Nobel Prize for brain research was Camillo Golgi in 1906, who shared the prize with Santiago Ramón y Cajal. Golgi developed a staining technique that allowed visualization of individual neurons. This technique was essential for Cajal's work. The first EEG recording from a human was made in 1924 by Hans Berger. This recording was a breakthrough in the study of brain activity. Berger's work opened up new avenues of research into sleep and neurological disorders. The fastest recorded reaction time is about 100 milliseconds, which is achieved by elite athletes. This incredibly fast response is the result of years of training. The brain can process information and initiate a response in a fraction of a second. The only mammal that cannot turn its head is the sloth, which has extra vertebrae in its neck. This anatomical limitation affects the brain's motor coordination. The sloth's limited neck mobility is compensated by its ability to rotate its body. The first brain surgery was performed by the ancient Egyptians, who practiced trepanation as early as 5,000 years ago. This procedure was likely used to treat head injuries or to release evil spirits. Evidence of trepanation has been found in skulls from many ancient cultures. The discovery of the role of neurons in brain function was a gradual process that involved many researchers. The neuron doctrine, which states that neurons are the basic units of the nervous system, was established in the early 20th century. This doctrine was essential for the development of modern neuroscience. The understanding of the brain's role in sleep has evolved significantly over time. Early researchers believed sleep was a passive state, a period of reduced brain activity. It is now understood that sleep is an active process that is essential for brain function. The first scientific studies of dreaming were conducted by Sigmund Freud, who interpreted dreams as expressions of unconscious desires. While many of Freud's theories have been discredited, he did help to establish that dreams are meaningful. His work influenced the development of psychology and neuroscience. The concept of the autonomic nervous system was first described in the late 19th century. This system regulates involuntary body functions such as heart rate and digestion. Understanding the autonomic nervous system was essential for understanding the brain's control of the body. The discovery of neurotransmitters, the chemicals that transmit signals between neurons, was a major breakthrough in neuroscience. The first neurotransmitter, acetylcholine, was discovered in the early 20th century. This discovery led to a deeper understanding of how the brain communicates. The development of the microscope allowed scientists to visualize neurons and their connections. Before the invention of the microscope, the brain was largely a mystery. The microscope was essential for the development of modern neuroscience. The first detailed description of the brain's structure was provided by the ancient Greek physician Galen, who believed that the brain was the seat of sensation and thought. While many of his theories were later disproven, his work was influential for centuries. The study of the brain has a long history, with contributions from many cultures and disciplines. Neuroscience is a relatively young field, but its roots go back to ancient times. The understanding of the brain has progressed significantly over the centuries. The first theory of memory proposed that memories were stored as physical impressions in the brain. This theory was proposed by Plato and was influential for centuries. It was not until the 19th century that a more sophisticated understanding of memory emerged. The concept of the unconscious mind was first popularized by Sigmund Freud, who proposed that much of our mental life occurs outside of conscious awareness. While Freud's theories are controversial, the idea of unconscious processes is now widely accepted. The brain processes vast amounts of information without conscious awareness. The first attempts to map the brain's functions were made by phrenologists in the 19th century. While phrenology was ultimately discredited, it contributed to the understanding of brain localization. The idea that different brain regions have different functions is a cornerstone of modern neuroscience. The study of brain development has a long history, with contributions from many researchers. The understanding of how the brain grows and develops is essential for understanding neurological disorders. Brain development is a complex and ongoing process. The first neurotransmitter to be discovered was acetylcholine, which plays a role in muscle contraction and memory. This discovery was a major breakthrough in understanding how the brain communicates. Neurotransmitters are essential for brain function. The first recordings of brain activity were made using electrodes placed on the scalp. These recordings are called electroencephalograms, or EEGs. EEGs are still used to diagnose sleep disorders and other conditions. The brain's complexity has made it one of the most difficult organs to study. However, advances in technology have led to significant progress in understanding the brain. Neuroscience is one of the most rapidly advancing fields of science. The history of brain research is a story of gradual progress, with many false starts and incorrect theories. This history reflects the difficulty of studying the brain. Despite these challenges, the understanding of the brain has advanced significantly. The doorway effect describes the phenomenon where walking through a doorway causes you to forget why you entered a room. This happens because the brain treats the doorway as a boundary or event boundary, clearing out the working memory that was holding your goal or intention. It is not a sign of memory failure, but a normal process of the brain compartmentalizing information by location. The effect is so reliable that it has been studied in multiple experiments, with participants consistently showing memory lapses after passing through a doorway. The brain uses these boundaries to segment experiences into separate episodes. Typing on a keyboard uses procedural memory, the system responsible for skills and habits that become automatic over time. Procedural memory is stored in the basal ganglia and cerebellum, rather than the hippocampus. This is why you can type without consciously thinking about where each letter is located. Reading text in all capital letters is harder to read, not easier, despite the common assumption that caps improve legibility. The brain recognizes words by their overall shape, and all caps text lacks the familiar shapes and contours of lowercase letters. This shape recognition is part of the brain's rapid reading process, which relies on familiar patterns. The brain predicts upcoming words while reading, a process called predictive coding. The brain uses context to anticipate what comes next, which is why you can often read a sentence that has missing letters or words. This predictive process makes reading faster and more efficient. People recognize their own face in mirrors faster than in photographs because mirrors provide a familiar flipped view. The brain has a mental representation of your own face, but it is based on the mirror image you see daily, not the unflipped image others see. This representation is stored in the visual cortex and can be activated rapidly. Writing by hand engages different brain areas than typing, involving more of the motor cortex and the sensory cortex. The act of forming individual letters requires fine motor control and attention to detail. This engagement is why writing by hand can enhance memory and learning compared to typing. The brain automatically distinguishes between a face and a non-face in as little as 100 milliseconds. This rapid processing is mediated by the fusiform face area, a region that responds selectively to faces. The brain is so attuned to faces that it can detect a face in a scene almost instantly, even before you are consciously aware of seeing one. Phantom vibration syndrome is the perception that your phone is vibrating when it is not. This phenomenon occurs because the brain becomes sensitized to the expected signal, a form of sensory conditioning. The brain is constantly monitoring for these alerts and can misinterpret other stimuli. The brain interprets the sound of rain as relaxing because it is a rhythmic, non-threatening auditory signal. Rain sounds have a consistent pattern with no sudden changes, which the brain processes as safe and predictable. This predictable rhythm can promote relaxation and sleep. Chewing gum can slightly improve recall and concentration, likely because it increases blood flow to the brain. The act of chewing also provides a mild arousal effect that can enhance alertness. However, the effect is modest and varies among individuals. The brain often ignores the nose in the field of vision, a phenomenon known as unconscious selective attention. The nose is always visible, but is filtered out of conscious awareness because it provides no useful information. This selective filtering is a common feature of the brain's processing. The name for the tip of a shoelace is an aglet, a small plastic or metal tube that prevents the lace from fraying. The brain processes this object as a common part of daily life and typically does not actively think about its function. This everyday object is a familiar part of the brain's environment. The brain processes the sound of your own voice differently from the voices of others, which is why hearing a recording of your voice can sound unfamiliar. When you speak, your brain receives internal auditory feedback, a combination of sound conducted through bone and through the air. The recording lacks this bone conduction, making your voice sound thinner and higher. The brain's association with objects extends to their function, with different brain regions processing object identity and object use. The brain recognizes a hammer by its shape, but also by its function as a tool for hitting things. This functional knowledge is stored in separate neural networks. The brain can identify an object by touch alone, a process called haptic recognition. The brain integrates sensory information from the skin and joints to form a mental representation of the object's shape. This ability allows you to find keys in your pocket without looking. The brain's spatial awareness is essential for reaching for objects, requiring coordination between visual and motor systems. The brain must calculate the distance and trajectory of the object to guide the arm accurately. This calculation is performed by the parietal cortex and the motor cortex. The brain can hold an object in your hand without needing constant visual input, a process called proprioception. Proprioception is the sense of the body's position in space, mediated by receptors in the muscles and joints. This sense allows you to maintain a grip on an object without looking at it. The brain's visual system can compensate for the obstruction of an object, allowing you to know that the object is still there, even if it is partially hidden. This is called visual completion, and it is a process performed by the visual cortex. The brain fills in the missing information based on context. The brain can anticipate the weight of an object based on its appearance, preparing the appropriate muscle force before you lift it. This anticipatory process is mediated by the motor cortex and the cerebellum. The brain adjusts the muscle force based on the expected weight. The brain's ability to recognize everyday objects is highly robust, even when objects are viewed from unusual angles. The brain can identify a mug or a shoe, even if it is upside down or rotated. This invariance is achieved through multiple visual representations. The brain's association with objects extends to their emotional significance, with objects becoming associated with positive or negative memories. A child's toy can evoke happy memories, while a medical instrument can evoke fear. This emotional association is mediated by the amygdala. The brain's spatial representation of objects is formed by combining visual, tactile, and auditory information. The brain integrates these sensory modalities to create a coherent representation of the environment. This integration is essential for interacting with objects. The brain can localize the position of an object in space by using visual and proprioceptive information. The parietal cortex integrates these signals to determine the object's location. This localization is essential for reaching and grasping. The brain can identify the orientation of an object in space, allowing you to align it with other objects. The brain processes the angle of an object relative to the vertical. This orientation processing is performed by the visual cortex. The brain's ability to perceive depth is essential for interacting with three-dimensional objects. The brain uses various cues, including binocular disparity, to determine depth. This depth perception is essential for reaching for objects. The brain can recognize the material of an object, such as metal or wood, by processing visual and tactile information. The brain uses texture and reflectance to determine the material. This material recognition is performed by the visual cortex. The brain's association with objects is essential for tool use, requiring the integration of motor and visual processing. The brain represents tools differently from other objects because they extend the body's capabilities. This tool representation is stored in the parietal cortex. The brain can learn the function of a new object by observing its use, a process called observational learning. The brain forms a representation of the object's function by watching others. This learning is mediated by the mirror neuron system. The brain can remember the location of objects, forming a spatial map of the environment. This spatial map is stored in the hippocampus and is essential for navigation. The brain can update this map as objects move. The brain's ability to recognize objects is essential for navigating the world, allowing you to identify familiar objects in your environment. This recognition is a fundamental cognitive ability. The brain is constantly processing visual information to identify objects. The brain's visual system can process objects in parallel, identifying multiple objects simultaneously. The brain is capable of parallel processing, with different areas processing different aspects of the visual scene. This parallel processing is essential for rapid object recognition. The brain's association with objects is influenced by attention, which can enhance or suppress object recognition. Attention is essential for processing visual information. The brain can selectively attend to certain objects, filtering out others. The brain's ability to recognize objects can be impaired by brain damage, a condition called agnosia. Agnosia is a deficit in object recognition, often resulting from damage to the visual cortex. The brain's ability to identify familiar objects is essential for everyday function. The brain's association with objects is a fundamental aspect of human cognition. The brain is constantly processing visual information, identifying objects in the environment. This processing is essential for interacting with the world. The brain's representation of objects is dynamic and can be updated with new information. The brain can learn new objects and update its representations. This learning is a continuous process. The brain's ability to recognize objects is one of its most remarkable achievements. The brain can identify a vast number of objects, each with unique features. This ability is essential for everyday life. The word oxymoron is itself an oxymoron, a term for a contradiction in terms that combines two opposing ideas. The word comes from the Greek words oxys, meaning sharp, and moros, meaning dull, literally, sharp dull. This self-referential quality makes it a favorite among linguists and word enthusiasts, a word that perfectly describes its own nature. The word book comes from the Germanic word for beech tree, a connection that reflects the early use of beech wood for writing surfaces. Before paper was widely available, Germanic peoples carved runes into beech wood tablets. Over time, the material gave its name to the object itself, a common pattern in language history where the medium becomes the word. The word barbarian originally meant anyone who did not speak Greek, carrying no negative connotation at first. To the ancient Greeks, foreign speech sounded like barbar, a kind of unintelligible babbling that they imitated. The word eventually evolved to mean someone uncivilized or uncultured, but its original sense was purely linguistic. The word hypocrite originally meant actor in ancient Greek, referring to someone who wore a mask and performed on stage. The root hypocrites described a theatrical performer, someone who pretended to be someone else. Over time, the meaning shifted to someone who pretends to be something they are not, a person who wears a metaphorical mask in daily life. The word sarcasm comes from the Greek word sarkazine, which means to tear flesh, a violent origin for such a common form of speech. This root reflects the sharp, cutting nature of sarcastic remarks, which can wound like a physical bite. The word itself carries the sense of a verbal wound, a linguistic attack that can leave a mark on its target. The word tragedy means goat song in Greek, a reference to the satyr plays that featured performers dressed as goat-like creatures. The connection between goats and tragic theatre is not entirely clear, but the word has persisted for over 2,000 years. Today, it retains none of its original goat-related associations, but the etymology remains a curious linguistic footnote. The word clue comes from the Old English clue, meaning a ball of thread, a reference to the myth of Theseus navigating the labyrinth. In that story, Theseus used a ball of thread to find his way out of the labyrinth after killing the Minotaur. The word evolved to mean anything that helps solve a puzzle or mystery, losing its literal thread connection but retaining its sense of guidance. The word muscle means little mouse in Latin, a description based on the appearance of a contracting bicep under the skin. Early anatomists thought the bulging muscle looked like a small mouse moving beneath the surface. The word musculus was adopted into English and has retained its animal association in a purely anatomical sense. The word salary comes from the Latin word for salt, salarium, a connection that reflects the historical value of this mineral. Roman soldiers were sometimes paid in salt or given a salt allowance as part of their compensation. The connection has been debated by historians, but the etymology remains a standard piece of linguistic trivia. The word emotion comes from the Latin emover, meaning to move out, a root that captures the sense of being moved by a feeling. The word evolved through French before entering English, retaining its core meaning of an inner movement or disturbance. This etymology reflects the ancient understanding of emotions as forces that move a person from within. The word person comes from the Latin persona, which originally meant a theatrical mask worn by actors in Roman theater. These masks indicated the character being portrayed, and the word came to mean the character itself. Over time, it shifted from the mask to the individual wearing it, a transition that reflects the way language evolves to meet new needs. The word trivia itself means crossroads, in Latin, a reference to the place where three roads met. In ancient times, crossroads were places where gossip and unimportant information were exchanged. From this origin, the word came to mean unimportant information or idle talk, a fitting name for a channel that embraces the trivial. The word sincere may come from the Latin sincerus, meaning clean or pure, though its exact origins are debated. There is a common myth that it comes from sine cera, meaning without wax, referring to dishonest merchants hiding flaws in pottery with wax filler. This explanation is widely repeated, but has no historical basis, making it a linguistic legend rather than a genuine etymology. The words salary and sauce both come from the same Latin root for salt, sal, a connection that shows how economic and culinary language overlap. Salt was a valuable commodity in ancient times, essential for preserving food and adding flavor. Words for payment and seasoning both trace back to this single essential mineral. The word luxury comes from the Latin luxuria, meaning excess or extravagance, a term that originally carried a negative moral judgment. Its original sense was associated with moral weakness and indulgence. Over time, it shifted to a neutral or even positive meaning, describing high quality or desirable goods. The word disaster comes from the Latin dis and astrum, meaning bad star, a reflection of the ancient belief that calamities were caused by unfavorable astrological events. The word retains this sense of misfortune, but has lost its connection to the stars in modern usage. Few people who use the word today are thinking about planetary alignments. The word candidate comes from the Latin candidatus, meaning dressed in white, a reference to the white togas worn by those seeking office in ancient Rome. These white garments symbolized purity and integrity, qualities that voters were supposed to associate with the candidate. The connection to clothing is now lost, but the word remains a standard term for someone seeking election. The word genius comes from the Latin genius, meaning a guardian spirit that was believed to guide each person in ancient Roman belief. This spirit was thought to influence a person's character and destiny. The word evolved to mean exceptional intellectual ability, leaving its spiritual origins behind while retaining a sense of innate gift. The word nice once meant foolish or stupid in Old French, a meaning that has shifted dramatically over centuries. It gradually passed through various meanings, including timid, refined, and precise, before arriving at its current positive sense. This semantic drift demonstrates how words can completely change their meaning over time. The word silly originally meant blessed or happy in Old English, a meaning that has shifted entirely over the centuries. It then shifted to mean innocent or naive, then to foolish, and eventually to ridiculous or absurd. This progression shows how language evolves through layers of meaning, each building on the last. The word nice and silly both demonstrate how words can drift from their original meanings over time. Language is constantly shifting, with words gaining and losing associations as culture changes. What a word means today is often quite different from what it meant centuries ago. The word clue and clue share a common origin, reflecting the way spelling can change while meaning remains stable. The word clue is still used in some contexts to mean a ball of thread, but clue has become the standard spelling for the metaphorical meaning. This split shows how words can diverge into different forms and meanings. The word muscle and mouse share a common Latin root, a connection that is invisible in modern English. The word musculus was the Latin word for both mouse and muscle, a homonym that caused some confusion in early anatomical texts. The English words have diverged in spelling but retain their shared origin. The words salary and soldier both come from the same Latin root for salt, sal, reflecting the importance of this mineral in Roman times. Soldiers were paid in salt, and the word for soldier, solidus, may also be related. This connection shows how economic and military language can share a common root. The word emotion and motion share a common root, reflecting the idea that emotions are a kind of movement. Both words come from the Latin movere, meaning to move. This connection captures the sense of emotions as forces that move a person from within. The word person and persona have a shared history, with persona originally meaning a theatrical mask. The word person evolved to mean an individual, while persona retained its association with character or role. This split shows how words can develop different meanings over time. The word trivia and trivial share a common root, with trivial meaning of little importance. Both words come from the Latin trivium, meaning crossroads. This connection reflects the idea that unimportant information was exchanged at crossroads. The word disaster and astronomy share a common root in astrum, meaning star. This connection reflects the ancient belief that the stars influenced human affairs. The word disaster means bad star, while astronomy means the study of stars. The word candidate and candid share a common root, with candid meaning honest or open. Both words come from the Latin candidus, meaning white. This connection reflects the association of white with purity and honesty. The word genius and genial share a common root in genius, meaning guardian spirit. The word genial originally meant related to a guardian spirit, and later came to mean cheerful or friendly. This connection shows how words can develop different meanings from a common root. The word nice and ignorant share a common origin in the Latin nescius, meaning ignorant. The word nice passed through various meanings before arriving at its current sense. The word ignorant is a more direct descendant of the same root. The words silly and saint share a common origin in the Latin sanctus, meaning holy or blessed. The word silly drifted from blessed to innocent to foolish, while saint retained its religious meaning. This split shows how words can diverge dramatically from a common root. The brain controls breathing automatically through a network in the brainstem called the respiratory center. This center generates a rhythmic pattern of nerve impulses that signals the diaphragm and chest muscles to contract and relax. You can override this automatic control by consciously holding your breath or breathing faster, but the brainstem will resume control the moment you stop paying attention. This automatic system operates continuously, day and night, without requiring any conscious effort. The brain regulates heart rate through the autonomic nervous system, which has two complementary branches. The sympathetic branch speeds up the heart in response to stress or activity, while the parasympathetic branch slows it down during rest. These two systems work in opposition, constantly adjusting the heart rate to match the body's current needs. The brain's medulla oblongata contains the cardiovascular center that coordinates this regulation. The brain controls digestion via the vagus nerve, which connects the brainstem to the digestive tract. This nerve sends signals that regulate the contractions of the stomach and intestines, as well as the release of digestive enzymes. The vagus nerve also carries sensory information back to the brain, providing feedback about the state of digestion. This communication is essential for coordinating the complex process of breaking down food. The brain initiates the release of adrenaline during stress through the sympathetic nervous system. When the brain perceives a threat, it signals the adrenal glands to release adrenaline into the bloodstream. This hormone prepares the body for action by increasing heart rate, dilating airways, and mobilizing energy stores. This response is often called the fight or flight reaction. The brain controls blinking automatically, with humans blinking about 15 to 20 times per minute. This rate is remarkably consistent across most healthy individuals. Blinking serves several purposes. It moistens the eye, removes debris, and gives the brain a brief moment of visual reset. The blink rate can increase or decrease depending on attention and environmental conditions. The brainstem is responsible for basic life support functions, including breathing, heart rate, and blood pressure regulation. This structure sits at the base of the brain, connecting the cerebrum to the spinal cord. Damage to the brainstem can be catastrophic because these automatic functions cannot be consciously controlled. The brainstem is one of the most evolutionarily ancient parts of the brain. The cerebellum contains more neurons than the rest of the brain combined, despite being much smaller in volume. This structure at the back of the head contains about 69 billion neurons, more than half of the brain's total. The cerebellum is primarily responsible for coordinating movement and balance, but it also plays a role in attention and language. Its large number of neurons reflects its computational demands. The brain's hypothalamus regulates body temperature, acting as the body's thermostat. This almond-sized structure detects changes in blood temperature and initiates responses to maintain a stable internal environment. When you are too hot, the hypothalamus triggers sweating and blood vessel dilation to release heat. When you are too cold, it triggers shivering and blood vessel constriction to conserve heat. The brain's pituitary gland controls growth and other endocrine functions, making it a central regulator of the hormonal system. This small gland, about the size of a pea, hangs below the hypothalamus and releases hormones that trigger other glands to produce their own hormones. The pituitary is sometimes called the master gland because its signals cascade throughout the body, influencing growth, metabolism, and reproduction. The brain is the primary organ that manages sleep-wake cycles, coordinating the activity of the pineal gland and other structures. This regulation involves the suprachiasmatic nucleus, which acts as the brain's master clock. The brain monitors light levels through the eyes and adjusts the timing of sleep accordingly. This system ensures that sleep and wakefulness occur at appropriate times of day. The brain receives signals about blood pressure from stretch receptors in the arteries, known as baroreceptors. These sensors detect changes in vessel wall tension and send information up to the brainstem. The brainstem then adjusts heart rate and blood vessel diameter to maintain stable pressure. This feedback loop operates constantly, keeping blood pressure within a narrow range. The brain controls the release of melatonin for sleep through the pineal gland, a small structure deep in the center of the brain. Melatonin is a hormone that signals when it is time to sleep, with production increasing in darkness and decreasing in light. The brain's suprachiasmatic nucleus coordinates this release, linking it to the light-dark cycle. This is why exposure to light in the evening can delay sleep onset. The brain's autonomic nervous system also controls pupil dilation, adjusting the amount of light entering the eye. The sympathetic branch dilates the pupils in low light or during arousal, while the parasympathetic branch constricts them in bright light. This regulation is automatic and occurs without conscious control. The brain is constantly adjusting pupil size to optimize vision. The brain's autonomic nervous system controls sweating, a process that helps regulate body temperature. Sweat glands are activated by the sympathetic nervous system in response to heat or stress. The evaporation of sweat from the skin cools the body. This cooling mechanism is one of the brain's primary ways of preventing overheating. The brain's autonomic nervous system controls salivation, regulating the production of saliva in response to food or anticipation of food. The parasympathetic branch stimulates salivation, while the sympathetic branch inhibits it. This regulation is automatic and occurs without conscious control. Saliva is essential for digestion and oral health. The brain's autonomic nervous system controls the release of digestive enzymes, coordinating the digestion of food. The brain signals the pancreas and other digestive organs to release enzymes when food is present. This signaling is mediated by the vagus nerve. The brain ensures that digestion occurs at the appropriate time. The brain's autonomic nervous system controls the bladder, regulating the storage and release of urine. The brain coordinates the relaxation of the bladder muscle and the contraction of the sphincter. This control is partially automatic and partially voluntary. The brain can delay urination but cannot prevent it indefinitely. The brain's autonomic nervous system controls the reproductive system, regulating sexual function and hormone release. This control is mediated by the hypothalamus and pituitary gland. The brain coordinates the release of hormones that regulate reproduction. This system is essential for fertility. The brain's autonomic nervous system controls the adrenal glands, which release adrenaline and other hormones. This control is mediated by the sympathetic nervous system. The adrenal glands are essential for the fight or flight response. The brain releases adrenaline in response to stress. The brain's autonomic nervous system controls the pancreas, regulating blood sugar levels. The pancreas releases insulin and glucagon in response to blood sugar levels. The brain's hypothalamus monitors blood sugar and signals the pancreas as needed. This regulation is essential for maintaining stable energy levels. The brain's autonomic nervous system controls the liver, regulating the storage and release of glucose. The liver releases glucose into the bloodstream when blood sugar is low. The brain signals the liver to release glucose as needed. This regulation is essential for brain function. The brain's autonomic nervous system controls the kidneys, regulating fluid balance and blood pressure. The kidneys filter blood and regulate fluid levels. The brain signals the kidneys to retain or release water as needed. This regulation is essential for maintaining stable blood pressure. The brain's autonomic nervous system controls the lungs, regulating airway diameter. The sympathetic branch dilates the airways, while the parasympathetic branch constricts them. This regulation is essential for breathing. The brain adjusts airway diameter in response to oxygen and carbon dioxide levels. The brain's autonomic nervous system controls the heart, regulating heart rate and force of contraction. The sympathetic branch increases heart rate and force, while the parasympathetic branch decreases them. This regulation is essential for maintaining blood pressure. The brain adjusts heart rate in response to activity and stress. The brain's autonomic nervous system controls blood vessels, regulating blood flow to different organs. The brain can constrict or dilate blood vessels to direct blood flow where it is needed. This regulation is essential for maintaining blood pressure and body temperature. The brain's autonomic nervous system controls the digestive system, regulating the movement of food through the digestive tract. The brain coordinates the contractions of the stomach and intestines. This regulation is essential for digestion and nutrient absorption. The brain's autonomic nervous system controls the tear glands, regulating tear production. The parasympathetic branch stimulates tear production. Tears are essential for lubricating and protecting the eyes. The brain controls tear production in response to eye irritation and emotion. The brain's autonomic nervous system controls the mucus glands, regulating mucus production in the respiratory and digestive tracts. Mucus is essential for protecting and lubricating these tracts. The brain controls mucus production in response to irritation and infection. The brain's autonomic nervous system controls the hair follicles, regulating hair erection, known as goosebumps. The sympathetic branch causes the erector pili muscles to contract, raising the hair. This response is a vestige of a mechanism that once made animals look larger. It is now largely a response to cold or emotion. The brain's autonomic nervous system controls the blood vessels in the skin, regulating blood flow to the skin. The brain can dilate or constrict these vessels to control heat loss. This regulation is essential for body temperature control. The brain adjusts skin blood flow in response to temperature changes. The brain's autonomic nervous system controls the sweat glands in the skin, regulating sweating. The sympathetic branch activates sweat glands in response to heat or stress. Sweating is essential for cooling the body. The brain controls sweating to maintain body temperature. The brain's autonomic nervous system controls the salivary glands, regulating saliva production. The parasympathetic branch stimulates salivation in response to food. Saliva is essential for digestion. The brain controls salivation to facilitate eating. The brain's autonomic nervous system controls the gastric glands, regulating stomach acid production. The brain signals the stomach to produce acid in response to food. Stomach acid is essential for digestion. The brain controls acid production to optimize digestion. The brain's autonomic nervous system controls the intestinal glands, regulating the release of digestive enzymes. The brain signals the intestines to release enzymes in response to food. These enzymes are essential for nutrient absorption. The brain controls their release to optimize digestion. The brain's autonomic nervous system controls the reproductive organs, regulating blood flow and hormone release. The brain coordinates the release of hormones that regulate reproduction. This regulation is essential for fertility. The brain controls reproductive function through the hypothalamic pituitary gonadal axis. The brain has specialized place cells in the hippocampus that fire when you are in a specific location. These cells create an internal map of your environment, with different place cells responding to different locations. When you move through a familiar space, these neurons fire in sequence, tracking your progress through the environment. The discovery of place cells earned John O'Keefe a Nobel Prize in 2014. Grid cells in the brain provide a coordinate system for mapping, forming a hexagonal grid that covers the environment. These cells, located in the entorhinal cortex, fire at regular intervals as you move through space, creating a mental grid that overlays the environment. This grid system allows the brain to calculate distances and directions between locations, making navigation possible even in unfamiliar terrain. The brain's map of the body is called the homunculus, a distorted representation that reflects the sensitivity and motor control of different body parts. The homunculus was first mapped by Wilder Penfield in the 1950s, who stimulated the brains of awake patients during surgery. The hands, face, and lips take up disproportionate amounts of the map, reflecting their high sensitivity and fine motor control. The brain can perceive locations of sounds via tiny differences in the time it takes sound to reach each ear. If a sound is slightly closer to the left ear, it arrives a fraction of a millisecond earlier, and the brain uses this delay to calculate the direction of the sound source. This process is so precise that humans can localize sounds to within a few degrees of accuracy. The brain adjusts for spatial distortion when reaching for objects, compensating for the fact that the arm moves in an arc while the target remains stationary. The brain must calculate the trajectory of the arm and predict where it will end up. This calculation involves the parietal cortex, which integrates visual and motor information. The brain combines vision and touch to map the body, integrating sensory information from multiple modalities. The brain uses visual input about the body's position and tactile input about the body's surface to create a unified representation. This integration is essential for tasks like reaching for objects while looking at your hands. The brain can remap body parts in conditions like phantom limb syndrome, where amputees feel sensation in a missing limb. This remapping occurs because the brain's map of the body is not fixed but can reorganize when sensory input changes. The brain may represent the missing limb as still present, leading to sensations that feel real even though the limb is gone. The brain's spatial awareness can be tricked by optical illusions, revealing the assumptions the brain makes about the visual world. The brain imposes order on ambiguous visual information, sometimes leading to perceptions that do not match reality. These illusions are not failures but examples of the brain's efficient processing. The brain uses landmarks to orient itself, relying on familiar objects to determine location. The brain processes landmark information through the parahippocampal place area, a region specialized for environmental recognition. This region is essential for navigating familiar environments, allowing you to recognize your surroundings and determine your position within them. The brain's ability to mentally rotate objects is called mental rotation, a cognitive process that allows you to imagine objects from different angles. This ability is essential for tasks like solving puzzles or understanding spatial relationships. The brain performs mental rotation through the parietal cortex, which processes spatial information. The brain's pathfinding ability declines with age, a natural part of the aging process. This decline occurs because the brain's spatial mapping systems become less efficient over time. However, the rate of decline varies widely between individuals, with some people maintaining their navigation skills well into old age. The brain processes near space and far space differently, using different neural systems for objects close to the body and those far away. The peripersonal space, the space immediately surrounding the body, is processed by the premotor cortex. The extrapersonal space, the space farther away, is processed by the parietal cortex. The brain's spatial map is stored in the hippocampus and is constantly updated as you move through the environment. This map is dynamic, with place cells firing in response to the current location. The brain can form new spatial maps for new environments, a process that takes time and repetition. The brain can learn the layout of a new environment through exploration, a process that involves the hippocampus and entorhinal cortex. As you move through a new space, the brain creates a cognitive map, gradually building a representation of the environment. This map is essential for navigation and orientation. The brain's spatial awareness is essential for everyday tasks like walking and reaching for objects. The brain must constantly process spatial information to guide movement. This processing occurs without conscious awareness, making it seem effortless. The brain's spatial processing is influenced by attention, which can enhance or suppress spatial awareness. Focusing on a specific location enhances processing in that area, while distraction reduces it. The brain's spatial processing is dynamic and context-dependent. The brain's spatial map is not a perfect representation of the environment, but a simplified version that captures essential features. The brain does not remember every detail, but represents key landmarks and distances. This simplification makes the map more efficient for navigation. The brain's spatial map can be distorted by factors like emotion and motivation, which can influence spatial awareness. Fear can make distances seem longer, while motivation can shorten them. These distortions reflect the brain's processing of spatial information. The brain's spatial processing is essential for memory and cognition, with spatial representations forming a framework for other types of information. The brain uses the hippocampus for spatial memory and other memory functions. This dual function makes the hippocampus essential for both navigation and memory. The brain's spatial processing is impaired by damage to the hippocampus and entorhinal cortex, which can cause difficulty with navigation and spatial memory. This impairment can affect the ability to find your way around familiar environments. Damage to these regions is a common feature of Alzheimer's disease. The brain's spatial awareness is essential for language and abstract thought, with spatial metaphors used to describe many concepts. The brain uses spatial representations to understand abstract ideas like time and hierarchy. This connection between space and cognition is a fundamental feature of human thought. The brain's spatial processing is influenced by experience and learning, with experts in navigation having enhanced spatial skills. Taxi drivers, for example, have larger hippocampi than the general population. This enlargement reflects the use of spatial skills in their profession. The brain's spatial awareness can be enhanced by training and practice, which can improve mental rotation and navigation skills. Spatial training can increase the size and activity of the hippocampus. This plasticity shows that the brain's spatial systems can change with experience. The brain's spatial processing is essential for tool use, requiring the representation of tools as extensions of the body. The brain represents tools in the same areas as the body, a process called tool incorporation. This incorporation allows you to use tools as if they were part of your own body. The brain's spatial map can be reorganized when sensory input changes, such as when someone wears prism goggles that shift vision. The brain can adapt to the altered visual input, compensating for the shift. This adaptation shows the brain's ability to update its spatial maps. The brain's spatial awareness is supported by the vestibular system, which provides information about balance and head position. The brain integrates vestibular signals with visual and proprioceptive information to create a unified sense of spatial orientation. This integration is essential for maintaining balance and posture. The brain's spatial processing is essential for social interaction, with spatial representations used to understand the positions of others. The brain processes the position of other people in relation to your own body. This processing is essential for understanding social interactions. The brain's spatial processing is influenced by culture, with different cultures having different spatial representations. Some cultures emphasize allocentric or map-based navigation, while others emphasize egocentric or body-based navigation. The brain adapts to these cultural differences. The brain's spatial awareness is essential for understanding maps and diagrams, which are external representations of spatial information. The brain processes maps by comparing them to its internal spatial representations. This processing is essential for using maps for navigation. The brain's spatial processing is impaired in conditions like spatial neglect, where patients ignore one side of space. Spatial neglect is caused by damage to the parietal cortex and is associated with difficulty attending to one side of the body. This condition demonstrates the brain's role in spatial attention. The brain's spatial map is updated by the head direction cells, which fire in response to the direction the head is pointing. These cells are located in the anterior thalamus and provide a directional compass for the brain. This directional system is essential for navigation. The brain's spatial processing is essential for dreaming, with dreams often involving spatial navigation. The brain uses the same spatial systems during dreaming as during waking. This suggests that spatial processing is a fundamental feature of brain function. The brain's spatial map is not a single map, but a network of maps that represent different aspects of space. The brain uses multiple maps for navigation, including place, grid, and head direction maps. This network provides a comprehensive representation of space. The brain's spatial awareness is essential for language comprehension, with the brain using spatial representations to understand spatial prepositions. The brain processes words like above and below by activating spatial representations. This shows the deep connection between language and spatial cognition. The brain's spatial processing is essential for mathematics, with spatial representations used to understand numbers and geometry. The brain uses the same systems for math as for spatial processing. This connection is why spatial skills are associated with mathematical ability. The brain's spatial map is constantly updated as you move through the environment, with the brain tracking your position and orientation. This constant updating is essential for navigating complex environments. The brain is always processing spatial information. The brain's spatial processing is a fundamental feature of cognition, supporting navigation, memory, and abstract thought. The brain's spatial systems are essential for everyday life, from finding your way to understanding language. Understanding spatial processing is essential for understanding the mind. The study of consciousness is one of the greatest challenges in neuroscience, with no single theory fully explaining how subjective experience arises from neural activity. Consciousness involves awareness of the self and the environment, a phenomenon that seems to emerge from the brain's complex networks. The neural correlates of consciousness are still being investigated, with researchers using brain imaging to study what happens in the brain during conscious awareness. The problem of consciousness is sometimes called the hard problem because it is so difficult to explain. The brain can recognize itself in a mirror, an ability that is present in humans and a few other animals. Mirror self-recognition develops in human infants at about 18 months of age and is a marker of self-awareness. The brain processes the image in the mirror as a representation of the self, not as another individual. This recognition requires the integration of visual and motor information. The brain can be tricked into thinking a rubber hand is its own, a phenomenon called the rubber hand illusion. In this illusion, a person watches a rubber hand being stroked, while their own hand is hidden and stroked simultaneously. The brain integrates the visual and tactile information, creating the sensation that the rubber hand is part of the body. This illusion demonstrates how the brain constructs the body schema based on sensory input. The brain constructs a body schema, an internal representation of the body's position and boundaries. The body schema is updated continuously through sensory input, integrating visual, tactile, and proprioceptive information. The brain uses this schema to guide movement and to distinguish the body from the environment. The body schema is flexible and can include tools that are used regularly. The brain's default mode network is active during daydreaming and self-referential thought, reflecting the brain's internal processing when not focused on external tasks. This network involves the medial prefrontal cortex, posterior cingulate cortex, and other regions that are active when you are thinking about yourself or others. The default mode network is associated with the narrative self, the story you tell about your own life. Its activity decreases during focused attention and increases during mind-wandering. The brain can have a sense of minimal self, the basic feeling of being a subject, distinct from the narrative self. The minimal self is the immediate sense of being the owner of one's experiences, a fundamental aspect of consciousness. This sense of self is present in infants and animals, preceding the development of the narrative self. The brain's sense of minimal self is associated with the activity of the insula and other regions. The brain's theory of mind allows us to infer the mental states of others, a capacity that is essential for social interaction. Theory of mind involves the ability to attribute beliefs, desires, and intentions to others. This ability is mediated by the temporoparietal junction and the medial prefrontal cortex. Theory of mind develops in childhood and is impaired in conditions like autism. The brain can be fooled into out-of-body experiences, where the sense of self seems to be located outside the physical body. These experiences can occur during sleep deprivation, sensory deprivation, or stimulation of the temporoparietal junction. Out-of-body experiences demonstrate that the sense of self is a construction of the brain. The brain can be tricked into locating the self in a different position. The brain's self-awareness is believed to involve the prefrontal cortex, which is essential for higher-order cognitive functions. The prefrontal cortex is the most recently evolved part of the brain and is associated with complex decision-making and planning. Damage to the prefrontal cortex can impair self-awareness and social cognition. This region is essential for the narrative self. The brain has a narrative self that tells a story of identity, providing a coherent sense of who you are over time. The narrative self is constructed through memories and experiences, creating a continuous sense of self. The brain's narrative self is essential for understanding your own life story. This narrative is shaped by culture and social interactions. The brain can have a preference for one's own name, a phenomenon called the cocktail party effect, where you can hear your name in a noisy room. The brain is constantly monitoring the environment for personally relevant information, such as your own name. This monitoring is mediated by the auditory cortex and the prefrontal cortex. The brain is more sensitive to your own name than to other names. The brain's default mode is associated with internally directed thought, reflecting the brain's tendency to engage in self-referential processing when not focused on external tasks. This internally directed thought is essential for creativity and self-reflection. The brain's default mode is active during daydreaming and mind-wandering. This activity is a normal part of brain function. The brain can have a sense of agency, the feeling that you are the author of your own actions. The sense of agency is a fundamental aspect of self-awareness, associated with the feeling of control over one's actions. The brain's sense of agency is mediated by the motor cortex and the parietal cortex. This sense of agency is essential for intentional action. The brain's sense of agency can be disrupted in conditions like schizophrenia, where patients may feel that their actions are controlled by external forces. This disruption reflects a failure of the brain's monitoring of action. The brain's sense of agency is a construction, not a direct perception. This construction can be altered by various factors. The brain can have a sense of ownership, the feeling that the body is your own. The sense of ownership is associated with the integration of sensory information from the body. The brain's sense of ownership is mediated by the parietal cortex and the insula. This sense of ownership is essential for self-awareness. The brain's sense of ownership can be disrupted in conditions like asomatognosia, where patients deny ownership of a body part. This disruption reflects a failure of the brain's body schema. The brain's sense of ownership is a construction, not a direct perception. This construction can be altered by brain damage. The brain can have a sense of familiarity, the feeling that a situation or person is familiar. The sense of familiarity is associated with the medial temporal lobe, which processes recognition memory. The brain's sense of familiarity is essential for social interaction. This sense of familiarity can be disrupted in conditions like déjà vu. The brain can experience déjà vu, the feeling that a situation is familiar even when it is not. Déjà vu is a common phenomenon that is not fully understood. It may involve the brain's memory systems activating inappropriately. Déjà vu is a normal experience that occurs in about 2/3 of people. The brain can have a sense of self-location, the feeling of being located in a specific place. The sense of self-location is essential for navigation and orientation. The brain's sense of self-location is mediated by the hippocampus and the parietal cortex. This sense of self-location is essential for understanding your position in space. The brain's sense of self-location can be disrupted in conditions like depersonalization, where people feel detached from their body. This disruption reflects a failure of the brain's sense of self. The brain's sense of self-location is a construction, not a direct perception. This construction can be altered by various factors. The brain can have a sense of self-continuity, the feeling that you are the same person over time. The sense of self-continuity is associated with memory and the narrative self. The brain's sense of self-continuity is essential for identity. This sense of continuity can be disrupted in conditions like dissociative identity disorder. The brain can have a sense of self-agency, the feeling that you are responsible for your own actions. The sense of self-agency is associated with the feeling of control. The brain's sense of self-agency is mediated by the motor cortex. This sense of agency is essential for intentional action. The brain can have a sense of self-esteem, the evaluation of your own worth. The sense of self-esteem is associated with the medial prefrontal cortex. The brain's sense of self-esteem is influenced by social interactions. This sense of self-esteem is essential for mental health. The brain can have a sense of self-efficacy, the belief in your own ability to succeed. The sense of self-efficacy is associated with the prefrontal cortex. The brain's sense of self-efficacy is influenced by experience. This sense of self-efficacy is essential for motivation. The brain can have a sense of self-identity, the feeling of who you are. The sense of self-identity is associated with memory and the narrative self. The brain's sense of self-identity is essential for understanding yourself. This sense of identity is shaped by culture and social interactions. The brain can have a sense of self-worth, the feeling that you are valuable. The sense of self-worth is associated with the medial prefrontal cortex. The brain's sense of self-worth is influenced by social interactions. This sense of self-worth is essential for mental health. The brain can have a sense of self-respect, the feeling that you deserve respect. The sense of self-respect is associated with the prefrontal cortex. The brain's sense of self-respect is influenced by experience. This sense of self-respect is essential for self-esteem. The brain can have a sense of self-determination, the feeling that you have control over your own life. The sense of self-determination is associated with the prefrontal cortex. The brain's sense of self-determination is influenced by experience. This sense of self-determination is essential for motivation. The brain can have a sense of self-compassion, the ability to be kind to yourself. The sense of self-compassion is associated with the insula and the prefrontal cortex. The brain's sense of self-compassion is influenced by social interactions. This sense of self-compassion is essential for mental health. The brain can have a sense of self-acceptance, the ability to accept yourself as you are. The sense of self-acceptance is associated with the medial prefrontal cortex. The brain's sense of self-acceptance is influenced by experience. This sense of self-acceptance is essential for self-esteem. The brain can have a sense of self-awareness, the ability to reflect on your own thoughts and feelings. The sense of self-awareness is associated with the prefrontal cortex. The brain's sense of self-awareness is essential for self-reflection. This sense of self-awareness is a fundamental aspect of human cognition. The brain can have a sense of self-consciousness, the awareness of being observed by others. The sense of self-consciousness is associated with the prefrontal cortex. The brain's sense of self-consciousness is influenced by social interactions. This sense of self-consciousness is essential for social behavior. The brain can have a sense of self-confidence, the belief in your own abilities. The sense of self-confidence is associated with the prefrontal cortex. The brain's sense of self-confidence is influenced by experience. This sense of self-confidence is essential for success. The brain's sense of self is a construction, not a fixed entity, but a dynamic process that is shaped by experience and context. The self is not a single thing, but a collection of processes that work together to create the experience of being a person. This construction is essential for understanding who you are. The brain creates the self from moment to moment, a continuous process that is fundamental to human experience. The sperm whale has the largest brain of any animal, weighing about 17 pounds, which is more than 5 times the weight of a human brain. This massive organ is essential for processing the complex sensory information that sperm whales receive in their deep ocean environment. The size of the brain reflects the demands of their underwater lives, requiring sophisticated navigation and communication systems. Despite its large size, the sperm whale's brain is not necessarily more intelligent than a human brain. A human brain is larger relative to body size than most other animals, a ratio that is often associated with higher cognitive abilities. The human brain-to-body mass ratio is about 1:40, which is higher than most mammals. This ratio is often used as an indicator of intelligence, though it is not a perfect measure. The human brain's large relative size is associated with complex cognitive abilities. Dolphins can recognize themselves in mirrors, indicating self-awareness, an ability that is rare in the animal kingdom. Mirror self-recognition has been demonstrated in dolphins, elephants, and some primates. This ability suggests that dolphins have a sense of self, which is a marker of higher cognitive function. The brain structures that support this ability are similar in dolphins and humans. Octopuses have neurons distributed throughout their arms, not just in their head, a unique feature of their nervous system. Each arm has its own mini-brain, allowing it to process information independently. This distributed nervous system allows octopuses to perform complex tasks with their arms. The octopus brain is one of the most unusual in the animal kingdom. The brain of a cat is about 1 inch long and weighs about 1 ounce, a small size relative to the cat's body. Despite its small size, the cat brain has similar structures to the human brain, including a cortex and hippocampus. The cat brain is often used in neuroscience research due to its similarities to the human brain. Its small size makes it easier to study in laboratory settings. An elephant's brain is larger than a human's, weighing about 11 pounds, but it has a smaller cortex relative to its total brain size. The elephant cortex is about half the size of the human cortex, despite the brain being much larger. The elephant brain is adapted for the elephant's social and environmental needs. The structure of the elephant brain reflects its evolutionary history. Some birds can remember the location of thousands of food caches, a remarkable feat of spatial memory. Birds like the Clark's nutcracker can hide and retrieve up to 30,000 seeds. This memory ability is associated with a larger hippocampus relative to brain size. The bird brain is capable of impressive memory feats despite its small size. The brain of a fruit fly has about 100,000 neurons, a tiny number compared to the human brain. Despite its small size, the fruit fly brain is capable of complex behaviors, including learning and memory. The fruit fly is a model organism in neuroscience research due to its simple nervous system. Its small size makes it easy to study genetically. Dogs can understand up to 250 words and gestures, a vocabulary comparable to a 2-year-old child. This understanding involves the processing of human language in the dog brain. The dog brain has been shaped by domestication, making it sensitive to human communication. Dogs are one of the few animals that can follow human pointing gestures. The octopus has 3 hearts and a brain shaped like a donut, with the esophagus passing through the center. The octopus brain is unusual in its structure, reflecting the octopus's unique evolutionary history. The donut shape allows the octopus to swallow large prey. This unusual anatomy is a product of the octopus's invertebrate lineage. Rats show empathy and will help other rats in distress, a behavior that is associated with the brain's social systems. Rats will free a trapped cage mate, even when there is no reward for doing so. This empathic behavior is mediated by the brain's oxytocin system. Rats are a model organism for studying social behavior. The brain of a bee is the size of a sesame seed, but can navigate complex routes, a remarkable feat of spatial processing. Bees can learn and remember the location of flowers, navigating through complex environments. The bee brain has about 1 million neurons, a small number for such complex behavior. The bee brain is a model for understanding simple navigation systems. The brain of a mouse weighs about 400 milligrams, a tiny size relative to the human brain. Despite its small size, the mouse brain has similar structures to the human brain, including a cortex and hippocampus. The mouse is a model organism in neuroscience research due to its genetic similarity to humans. Its small size makes it easy to study in laboratory settings. The brain of a chimpanzee is about 1/3 the size of the human brain, but it has similar structures and functions. The chimpanzee brain has a similar cortex to the human brain, though it is smaller. The chimpanzee is a close evolutionary relative of humans, sharing about 98% of its DNA. The chimpanzee brain is used to study the evolution of human cognition. The brain of a crow is about the size of a human thumb, but crows can solve complex problems and use tools. The crow brain is relatively large for a bird, reflecting its advanced cognitive abilities. Crows can make and use tools to extract food. The crow brain is a model for studying avian intelligence. The brain of an ant has about 250,000 neurons, a tiny number for such a complex social insect. Despite its small size, the ant brain can process pheromone signals and navigate complex environments. The ant brain is adapted for social living, coordinating the activities of the colony. The ant brain is a model for understanding social behavior. The brain of a parrot is relatively large for a bird, supporting its advanced cognitive abilities. Parrots can learn to mimic human speech and perform complex tasks. The parrot brain has a large cortex-like structure called the dorsal ventricular ridge. This structure is involved in higher cognitive functions in birds. The brain of an elephant has a highly folded cortex with many convolutions that increase surface area. This folding is associated with higher cognitive abilities, allowing more neurons to be packed into a limited volume. The elephant brain is adapted for the elephant's complex social and environmental needs. The folding of the cortex is a marker of cognitive complexity. The brain of a pig is similar in structure to a human brain, making it a model organism for studying human brain diseases. The pig brain has a similar cortex and hippocampus to the human brain. The pig is often used in neuroscience research due to its anatomical similarities to humans. Its size makes it easier to study in laboratory settings. The brain of a rat has about 200 million neurons, a small number compared to the human brain. Despite its small size, the rat brain can perform complex behaviors, including learning and memory. The rat is a model organism in neuroscience research due to its genetic similarity to humans. Its small size makes it easy to study in laboratory settings. The brain of a monkey has about 6 billion neurons, a number that is intermediate between humans and rats. The monkey brain has similar structures to the human brain, including a large cortex. Monkeys are used in neuroscience research to study higher cognitive functions. The monkey brain is a model for understanding human brain function. The brain of a whale has a highly folded cortex, reflecting its advanced cognitive abilities. The whale brain is adapted for the whale's complex social and environmental needs. Whales are known for their complex vocalizations and social structures. The whale brain is one of the largest in the animal kingdom. The brain of a dolphin has a large cortex, supporting its advanced cognitive abilities. Dolphins are known for their complex social behaviors and vocalizations. The dolphin brain is similar in structure to the human brain, though it is larger. Dolphins are one of the most intelligent animals on Earth. The brain of a bird has a structure called the dorsal ventricular ridge, which is involved in higher cognitive functions. This structure is similar to the cortex in mammals. The bird brain is capable of complex behaviors, including tool use and problem solving. The bird brain is a model for studying avian intelligence. The brain of a reptile has a simpler structure than the mammalian brain, with a less developed cortex. Reptiles are capable of basic behaviors but lack the complex cognitive abilities of mammals. The reptile brain is a model for understanding the evolution of the brain. Its simple structure makes it easier to study. The brain of a fish has a relatively simple structure, with a less developed cortex. Fish are capable of basic behaviors, including learning and memory. The fish brain is a model for understanding the evolution of the brain. Its simple structure makes it easier to study. The brain of an amphibian has a simpler structure than the mammalian brain, with a less developed cortex. Amphibians are capable of basic behaviors, but lack the complex cognitive abilities of mammals. The amphibian brain is a model for understanding the evolution of the brain. Its simple structure makes it easier to study. The brain of an insect has a simple structure, with a small number of neurons. Insects are capable of basic behaviors, including navigation and social interaction. The insect brain is a model for understanding simple nervous systems. Its small size makes it easy to study genetically. The brain of a worm has about 300 neurons, a tiny number for a multicellular organism. Despite its small size, the worm brain can perform basic behaviors, including movement and feeding. The worm brain is a model for understanding the nervous system. Its simple structure makes it easy to study genetically. The brain of a mollusk, such as a snail, has about 10,000 neurons, a small number for a multicellular organism. Despite its small size, the mollusk brain can perform basic behaviors, including learning and memory. The mollusk brain is a model for understanding simple nervous systems. Its simple structure makes it easy to study. The brain of a crustacean, such as a crab, has about 100,000 neurons, a small number for a multicellular organism. Despite its small size, the crustacean brain can perform basic behaviors, including navigation and social interaction. The crustacean brain is a model for understanding simple nervous systems. The brain of a spider has about 100,000 neurons, a small number for a multicellular organism. Despite its small size, the spider brain can perform complex behaviors, including web building and hunting. The spider brain is a model for understanding simple nervous systems. The brain of an octopus has about 500 million neurons, a relatively large number for an invertebrate. This large number supports the octopus's complex behaviors, including problem-solving and camouflage. The octopus brain is one of the most complex in the invertebrate world. It is a model for understanding the evolution of intelligence. Glucose is the brain's primary fuel source, providing the energy needed for all neural activity. The brain cannot use fats or proteins directly for energy, relying instead on glucose from the bloodstream. This dependence on glucose is why blood sugar levels have such a significant impact on cognitive function. Without adequate glucose, the brain cannot maintain its normal activity levels. The brain cannot store glucose and requires a constant supply from the bloodstream. Unlike muscles, which can store glycogen for later use, the brain has limited storage capacity. This means that even brief drops in blood sugar can affect cognitive performance. The brain relies on the liver to maintain stable blood glucose levels. Caffeine blocks adenosine receptors, reducing the feeling of tiredness and promoting wakefulness. Adenosine is a neurotransmitter that builds up during waking hours, promoting sleepiness. By blocking adenosine receptors, caffeine prevents the brain from detecting this sleep signal. This is why caffeine makes you feel more alert and awake. Omega-3 fatty acids are important for brain structure and function, forming a key component of cell membranes. These fatty acids are essential for the brain's development and maintenance. A diet rich in omega-3s has been associated with better cognitive function and reduced risk of cognitive decline. The brain cannot produce omega-3s and must obtain them from the diet. The smell of rosemary has been linked to improved memory in some studies, though the effect is modest. The aroma of rosemary contains compounds that may enhance cognitive performance. This effect is thought to be mediated by the olfactory system, which connects directly to memory centers. The improvement is small but measurable in some experimental settings. Dark chocolate contains small amounts of compounds that may improve mood and cognitive function. These compounds include flavonoids and theobromine, which have mild stimulant effects. The improvement is modest and short-lived. Dark chocolate is often cited as a brain-healthy food due to its antioxidant content. Eating breakfast has been associated with better cognitive performance in some studies, particularly in children. Breakfast provides glucose to the brain after the overnight fast, restoring energy levels. This effect is most pronounced in the morning, when the brain's glucose levels are lowest. The cognitive benefits of breakfast include improved attention and memory. The brain uses about 20% of the body's calories, despite its small size, reflecting its high metabolic demands. This significant energy consumption is necessary for maintaining neural activity. The brain is one of the most energy-hungry organs in the body. This high-calorie consumption is why the brain is sensitive to changes in blood sugar. Dehydration can impair mood and concentration, even at mild levels of fluid loss. The brain is sensitive to changes in hydration status, with even a 2% loss affecting cognitive function. This effect is thought to be due to changes in brain volume and blood flow. Staying hydrated is essential for maintaining cognitive performance. Spicy food triggers the brain's pain receptors, releasing endorphins that can create a feeling of pleasure. Capsaicin, the compound that makes chili peppers hot, activates the same receptors that respond to heat and pain. The brain responds to this signal by releasing endorphins, which can produce a mild euphoria. This is why many people enjoy eating spicy food. The brain responds to sugar similarly to some rewarding stimuli, activating the brain's reward system. Sugar consumption causes the release of dopamine, a neurotransmitter associated with pleasure and motivation. This is why sugary foods can be so appealing, and why they can be difficult to resist. The brain's reward system is designed to encourage the consumption of energy-dense foods. Green tea contains L-theanine, an amino acid that may promote relaxation without causing drowsiness. L-theanine increases the production of alpha waves in the brain, which are associated with relaxed alertness. This compound is thought to work by increasing the levels of GABA, an inhibitory neurotransmitter. The combination of L-theanine and caffeine in green tea can promote a state of calm focus. The brain's response to food is influenced by the gut microbiome, which communicates with the brain through the gut-brain axis. The microbiome produces neurotransmitters and other compounds that affect brain function. This communication is mediated by the vagus nerve and the immune system. The gut-brain axis is an area of active research in neuroscience. The brain processes the taste of food through a combination of taste receptors and olfactory signals. Taste is a multisensory experience, combining gustatory, olfactory, and even tactile information. The brain integrates these signals to create the perception of flavor. This integration is essential for enjoying food. The brain's hunger signals are regulated by the hypothalamus, which monitors blood glucose and hormone levels. The hypothalamus responds to changes in these signals by initiating hunger or satiety. Ghrelin is a hormone that stimulates hunger, while leptin suppresses it. The brain's hunger system is designed to maintain energy balance. The brain's satiety signals are also regulated by the hypothalamus, which responds to signals from the digestive system. The brain receives information about the stomach's fullness and the nutrient content of food. This information is transmitted through the vagus nerve and hormones. The brain's satiety system is essential for preventing overeating. The brain's reward system is activated by eating, particularly by foods that are high in fat and sugar. This response is adaptive, encouraging the consumption of energy-dense foods. However, in modern environments, this system can lead to overeating. The brain's reward system is a major factor in food choices. The brain's response to food is influenced by learning and experience, with preferences developing over time. The brain learns to associate certain foods with pleasure or aversion. This learning is mediated by the reward system and the hippocampus. Food preferences are shaped by both biology and culture. The brain's olfactory system is closely linked to memory and emotion, which is why smells can trigger powerful memories. The olfactory bulb connects directly to the amygdala and hippocampus. This direct connection is why certain food smells can evoke vivid memories. The brain's response to food is strongly influenced by emotional associations. The brain's taste receptors are located on the tongue, but the brain processes taste information in the gustatory cortex. This cortex integrates taste information with other sensory inputs. The brain's representation of taste is not a simple map, but a complex network. This network is essential for the perception of flavor. The brain's response to food is influenced by visual cues, such as the appearance of food. The brain processes visual information about food, activating the reward system. This is why food presentation can affect how much you enjoy a meal. The brain's response to food is multisensory. The brain's response to food is influenced by social context, with people eating more in social settings. The brain's social systems interact with the reward system to influence eating behavior. This social influence is a major factor in eating patterns. The brain's response to food is not just a physiological process, but also a social one. The brain's response to food is influenced by stress, with stress often leading to overeating. The brain's stress response can increase the desire for high-calorie foods. This is thought to be due to the effects of cortisol on the reward system. Stress eating is a common response to emotional distress. The brain's response to food is influenced by sleep, with sleep deprivation leading to increased hunger. Sleep deprivation affects the hormones that regulate hunger, increasing ghrelin and decreasing leptin. This hormonal change can lead to overeating. The brain's response to food is influenced by sleep quality. The brain's response to food is influenced by exercise, which can reduce appetite in some people. Exercise affects the hormones that regulate hunger, reducing ghrelin levels. This effect is thought to be mediated by the hypothalamus. The brain's response to food is influenced by physical activity. The brain's response to food is influenced by the time of day, with hunger patterns following circadian rhythms. The brain's internal clock regulates hunger and satiety signals. This circadian regulation is mediated by the suprachiasmatic nucleus. The brain's response to food is influenced by the time of day. The brain's response to food is influenced by the temperature of food, with cold and hot foods being processed differently. The brain's temperature receptors are activated by food temperature, influencing the perception of flavor. This is why some foods are better served at specific temperatures. The brain's response to food is influenced by thermal cues. The brain's response to food is influenced by the texture of food, with the brain processing the mouthfeel of food. The brain's tactile receptors in the mouth provide information about the texture of food. This texture information is integrated with taste and smell to create the perception of flavor. The brain's response to food is multisensory. The brain's response to food is influenced by the color of food, with the brain expecting certain colors to correspond to specific tastes. The brain's visual system processes the color of food, influencing expectations. This is why food coloring is used to enhance the appearance of food. The brain's response to food is influenced by visual cues. The brain's response to food is influenced by the sound of food, with the brain processing the crunch or sizzle of food. The brain's auditory system provides information about the texture of food. This auditory information is integrated with other sensory inputs. The brain's response to food is multisensory. The brain's response to food is influenced by the context in which it is eaten, with the brain associating certain foods with certain settings. This contextual learning is mediated by the hippocampus. The brain's response to food is influenced by past experiences. This is why some foods are comfort foods. The brain's response to food is influenced by the availability of food, with the brain adjusting hunger signals based on food availability. The brain's hunger system is designed to maintain energy balance. This system is influenced by environmental cues. The brain's response to food is adaptive. The brain's response to food is influenced by the taste of food, with the brain processing sweet, sour, salty, bitter, and umami. These basic tastes are detected by taste receptors on the tongue. The brain integrates these taste signals to create the perception of flavor. The brain's response to food is essential for survival. Barometric pressure changes can affect mood and joint pain, with many people reporting increased discomfort when pressure drops. The brain responds to these pressure changes through the vestibular system and baroreceptors. This sensitivity is thought to be related to the body's response to atmospheric pressure fluctuations. The connection between weather and mood is well documented but not fully understood. Sunlight triggers the brain to produce serotonin, a neurotransmitter that regulates mood and well-being. The brain's production of serotonin increases with exposure to bright light. This is why many people feel more energetic and positive on sunny days. The effect is mediated by the brain's visual system and the pineal gland. Seasonal affective disorder is linked to reduced sunlight in winter months, leading to decreased serotonin production and increased melatonin. This condition is associated with depression, fatigue, and social withdrawal. The brain's response to light is mediated by the suprachiasmatic nucleus, which regulates the circadian rhythm. Light therapy is often used to treat this condition. The brain can detect changes in temperature as small as 0.5 degrees Celsius, a sensitivity essential for maintaining body temperature. This detection is mediated by thermoreceptors in the skin and the brain's hypothalamus. The brain responds to these changes by initiating appropriate thermoregulatory responses. This sensitivity is essential for survival. Humidity can affect the brain's ability to cool the body through evaporation, impacting cognition and physical performance. High humidity reduces the efficiency of sweating, making it harder to maintain a stable body temperature. This can lead to fatigue and reduced cognitive function. The brain's thermoregulatory system is sensitive to humidity levels. The sound of thunderstorms can be calming due to the brain's perception of low-frequency rumbles as non-threatening. The brain processes these sounds as predictable and rhythmic, promoting relaxation. This is why many people find the sound of rain and thunder soothing. The brain's auditory system responds to these sounds by reducing stress. The brain's circadian rhythm is influenced by the light-dark cycle of the Earth, which provides the primary time cue for the internal clock. The brain's suprachiasmatic nucleus receives light information from the eyes and synchronizes the body's rhythms accordingly. This synchronization is essential for maintaining a consistent sleep schedule. The brain's internal clock is slightly longer than 24 hours, but is reset daily by light. Altitude sickness occurs because the brain is sensitive to oxygen levels, with low oxygen impairing cognitive function. At high altitudes, the brain receives less oxygen, leading to symptoms like headache, fatigue, and confusion. The brain's sensitivity to oxygen is a result of its high metabolic demands. This sensitivity is why altitude sickness can be dangerous. Wind speed can subtly affect mood and activity levels, with many people feeling more energetic on windy days. The brain's response to wind is mediated by the somatosensory system and the vestibular system. This response is thought to be related to the brain's processing of environmental stimuli. The connection between wind and mood is not fully understood. The brain can perceive the passing of seasons without a clock, using changes in light and temperature as cues. The brain's internal clock is influenced by the changing day length and temperature. This seasonal sensitivity is essential for regulating seasonal behaviors. The brain's response to seasons is mediated by the suprachiasmatic nucleus. The geomagnetic field is not directly perceived by human brains, unlike some animals that use it for navigation. While humans do not have a magnetic sense, some studies suggest that the brain may respond to magnetic fields. This response is not well understood and is an area of ongoing research. The brain's sensitivity to geomagnetic fields is debated. Rainy days can reduce serotonin levels in some individuals, leading to lower mood and energy. The brain's production of serotonin is influenced by light exposure, which is reduced on cloudy days. This is why some people experience mood changes on rainy days. The effect is thought to be mediated by the brain's visual system. The brain's response to weather is influenced by individual differences, with some people being more sensitive to weather changes than others. These differences are thought to be related to variations in the brain's response to environmental stimuli. Some people are more prone to weather-related mood changes. The brain's sensitivity to weather is a normal part of human variation. The brain's response to temperature is mediated by the hypothalamus, which acts as the body's thermostat. The hypothalamus receives temperature information from the skin and the blood. This information is used to initiate appropriate thermoregulatory responses. The hypothalamus is essential for maintaining a stable body temperature. The brain's response to light is mediated by melanopsin, a photopigment found in the eye. Melanopsin detects blue light, signaling the brain to suppress melatonin production. This is why exposure to blue light in the evening can delay sleep onset. The brain's response to light is essential for regulating the circadian rhythm. The brain's response to weather is influenced by the autonomic nervous system, which regulates the body's response to environmental changes. The autonomic nervous system is essential for maintaining homeostasis. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the endocrine system, which releases hormones in response to environmental changes. The endocrine system is essential for regulating the body's response to stress. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the immune system, which can be affected by weather changes. The immune system is essential for fighting infection. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the cardiovascular system, which can be affected by temperature changes. The cardiovascular system is essential for maintaining blood flow. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the respiratory system, which can be affected by air quality and temperature. The respiratory system is essential for oxygen exchange. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the musculoskeletal system, which can be affected by temperature and humidity. The musculoskeletal system is essential for movement. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the digestive system, which can be affected by temperature and food availability. The digestive system is essential for nutrient absorption. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the reproductive system, which can be affected by seasonal changes. The reproductive system is essential for reproduction. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the skin, which provides information about temperature and humidity. The skin is essential for thermoregulation. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the ears, which provide information about sound and balance. The ears are essential for hearing and balance. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the eyes, which provide information about light and visual stimuli. The eyes are essential for vision. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the nose, which provides information about smell and air quality. The nose is essential for olfaction. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the tongue, which provides information about taste. The tongue is essential for taste. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the nervous system, which processes information from all the senses. The nervous system is essential for perception and action. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by the brain itself, which integrates information from all the senses. The brain is essential for processing environmental information. The brain's response to weather is a complex process involving multiple systems. The brain's response to weather is influenced by genetics, which determine individual sensitivity to weather changes. Genetics are essential for determining individual variation. The brain's response to weather is a complex process involving multiple factors. The brain's response to weather is influenced by experience, which shapes the brain's response to environmental stimuli. Experience is essential for learning and adaptation. The brain's response to weather is a complex process involving multiple factors. The brain's response to weather is influenced by culture, which shapes the brain's response to environmental stimuli. Culture is essential for shaping behavior. The brain's response to weather is a complex process involving multiple factors. The brain's response to weather is influenced by context, which shapes the brain's response to environmental stimuli. Context is essential for understanding the environment. The brain's response to weather is a complex process involving multiple factors. The brain's response to weather is influenced by expectation, which shapes the brain's response to environmental stimuli. Expectation is essential for perception. The brain's response to weather is a complex process involving multiple factors. The brain's response to weather is influenced by attention, which shapes the brain's response to environmental stimuli. Attention is essential for focusing on relevant stimuli. The brain's response to weather is a complex process involving multiple factors. The brain's response to weather is influenced by emotion, which shapes the brain's response to environmental stimuli. Emotion is essential for survival. The brain's response to weather is a complex process involving multiple factors. The brain's response to weather is influenced by motivation, which shapes the brain's response to environmental stimuli. Motivation is essential for goal-directed behavior. The brain's response to weather is a complex process involving multiple factors. The brain's response to weather is influenced by memory, which shapes the brain's response to environmental stimuli. Memory is essential for learning and adaptation. The brain's response to weather is a complex process involving multiple factors. The brain's response to weather is a fundamental aspect of human experience, reflecting the brain's constant interaction with the environment. The brain is always processing environmental information, integrating signals from all the senses. This processing is essential for survival and well-being. The brain's response to weather is a testament to its complexity and adaptability. The brain's reaction time can be improved by playing video games, particularly action games that require rapid responses. Gamers often show faster reaction times and better visual attention than non-gamers. This improvement is thought to be due to the brain's plasticity, which allows it to adapt to the demands of the game. The effect is most pronounced in games that require quick decision-making. Athletes often use mental imagery to improve performance, visualizing themselves executing a skill successfully. This visualization activates the same brain regions that are involved in actually performing the skill. Mental imagery is a form of motor learning that can enhance physical performance. The brain's motor system is activated by imagining movement even without physical execution. The brain releases endorphins during exercise, reducing pain perception and creating a feeling of euphoria. Endorphins are natural opioids that bind to the same receptors as morphine. This release is thought to be responsible for the runner's high that many athletes experience. The brain's endorphin system is activated by prolonged exercise. The zone, or flow state, is a mental state of complete absorption, where the brain is fully engaged in the task at hand. In this state, the brain's activity is highly focused, with reduced activity in the prefrontal cortex. This reduced activity is associated with a sense of effortless action. The flow state is often described as being in the zone. Chess players can burn up to 6,000 calories a day during tournaments, reflecting the brain's high energy demands. This calorie burn is due to the intense cognitive activity required for competitive chess. The brain's energy consumption increases during complex mental tasks. Chess players often lose weight during tournaments. The brain's motor cortex is highly active during sports performance, coordinating the movements of the body. The motor cortex is responsible for planning and executing voluntary movements. This area is essential for athletic performance. The motor cortex is highly active during practice and competition. Performance anxiety involves the brain's fear response system, which can interfere with athletic performance. The amygdala is activated in response to perceived threat, triggering the fight or flight response. This response can lead to physical symptoms like increased heart rate and sweating. Performance anxiety is a common challenge for athletes. The brain predicts the trajectory of a ball based on visual cues, allowing athletes to anticipate where the ball will be. This prediction is mediated by the brain's visual system and the parietal cortex. The brain uses past experience to predict future trajectories. This predictive ability is essential for catching and hitting a ball. Esports players have been shown to have faster reaction times than non-players, reflecting the demands of competitive gaming. Esports players also show enhanced visual attention and decision-making skills. These improvements are thought to be due to the brain's plasticity. Esports is a growing field in sports psychology. The brain's reward system is activated by winning, releasing dopamine and creating a feeling of pleasure. This release reinforces the behavior that led to the win, encouraging future success. The brain's reward system is essential for motivation and learning. Winning activates the same reward pathways as other pleasurable experiences. Learning a new sport creates new neural pathways, reflecting the brain's ability to adapt to new challenges. The brain's motor system reorganizes in response to new skills. This reorganization is a form of neuroplasticity. Learning a new sport can improve cognitive function. The brain's decision-making speed is critical in high-speed sports, where split-second decisions can determine the outcome. The brain must process visual information and initiate a response in a fraction of a second. This speed is mediated by the brain's motor and visual systems. Fast decision-making is essential for success in many sports. The brain's hand-eye coordination is essential for sports that involve hitting or catching a ball. The brain must integrate visual and motor information to guide the hand to the correct position. This coordination is mediated by the parietal cortex. Hand-eye coordination is a fundamental skill in many sports. The brain's proprioceptive system provides feedback about the body's position in space, essential for athletic performance. Proprioception is the sense of the body's position, mediated by receptors in the muscles and joints. This feedback is essential for maintaining balance and coordination. Proprioception is often trained in sports. The brain's visual system processes the speed and direction of moving objects, essential for tracking a ball or opponent. The brain's visual cortex is highly active during sports performance. This processing is essential for anticipating movement. The brain's visual system is adapted for tracking moving objects. The brain's auditory system processes sounds like the crack of a bat or the whistle of a referee, providing important cues. The brain's auditory cortex processes these sounds, integrating them with visual information. This integration is essential for responding to auditory cues. The brain's auditory system is important in many sports. The brain's somatosensory system processes touch and pressure, providing feedback about the body's interaction with the environment. The brain's somatosensory cortex processes this information. This feedback is essential for adjusting movement. The somatosensory system is important in sports that involve contact. The brain's vestibular system processes information about balance and head position, essential for maintaining stability. The brain's vestibular system is located in the inner ear. This system is essential for sports that involve rapid movement. The vestibular system is often trained in sports. The brain's limbic system is involved in the emotional aspects of sports, including motivation and arousal. The brain's limbic system is essential for regulating emotion. This system is important for maintaining focus and motivation. The limbic system is activated during competition. The brain's prefrontal cortex is involved in strategic thinking and decision-making, essential for sports that require planning. The brain's prefrontal cortex is essential for higher cognitive functions. This area is active during strategic thinking. The prefrontal cortex is important for success in many sports. The brain's hippocampus is involved in spatial memory, essential for navigation in sports like soccer or basketball. The brain's hippocampus is essential for spatial processing. This area is active during navigation. The hippocampus is important for spatial awareness in sports. The brain's cerebellum is involved in motor coordination and learning, essential for sports that require precise movements. The brain's cerebellum is essential for motor control. This area is active during practice and performance. The cerebellum is important for learning new skills. The brain's basal ganglia are involved in motor learning and habit formation, essential for sports that require automatic movements. The brain's basal ganglia are essential for procedural memory. This area is active during automatic movements. The basal ganglia are important for sports that require routine. The brain's anterior cingulate cortex is involved in error detection, essential for correcting mistakes in sports. The brain's anterior cingulate cortex is essential for monitoring performance. This area is active when errors are detected. The anterior cingulate cortex is important for learning from mistakes. The brain's insula is involved in body awareness, essential for sports that require precise control. The brain's insula is essential for interoception. This area is active during body awareness. The insula is important for sports that require fine control. The brain's mirror neuron system is involved in observational learning, allowing athletes to learn by watching others. The brain's mirror neurons are activated by observing actions. This system is essential for social learning. Mirror neurons are important for learning new skills. The brain's reward system is activated by winning, creating a feeling of pleasure that reinforces competitive behavior. The brain's reward system is essential for motivation. This system is activated by success. The reward system is important for sports performance. The brain's stress response is activated by competition, releasing cortisol and adrenaline. The brain's stress response is essential for mobilizing energy. This response is activated by perceived threat. The stress response is important for sports performance. The brain's cognitive control is essential for sports that require focus and attention, allowing athletes to block out distractions. The brain's cognitive control system is essential for maintaining focus. This system is active during competition. Cognitive control is important for sports performance. The brain's working memory is essential for sports that require remembering plays or strategies. The brain's working memory is essential for short-term retention. This system is active during planning. Working memory is important for sports that require strategy. The brain's long-term memory is essential for sports that require remembering skills and strategies. The brain's long-term memory is essential for retention. This system is active during recall. Long-term memory is important for sports performance. The brain's sensory integration is essential for sports that require combining information from multiple senses. The brain's sensory integration system is essential for perception. This system is active during complex tasks. Sensory integration is important for sports performance. The brain's motor planning is essential for sports that require executing complex movements. The brain's motor planning system is essential for action. This system is active during planning. Motor planning is important for sports performance. The brain's executive functions are essential for sports that require decision-making and problem-solving. The brain's executive functions are essential for higher cognition. This system is active during complex tasks. Executive functions are important for sports performance. The brain's attention system is essential for sports that require maintaining focus over time. The brain's attention system is essential for concentration. This system is active during sustained tasks. Attention is important for sports performance. The brain's cognitive reserve is essential for sports that require mental endurance. The brain's cognitive reserve is essential for resilience. This system is active during sustained effort. Cognitive reserve is important for sports performance. The brain's adaptability is essential for sports that require adjusting to changing conditions. The brain's plasticity allows it to adapt to new challenges. This adaptability is essential for success in sports. The brain's ability to adapt is a key factor in athletic performance. The bystander effect is the brain's tendency to not help if others are present, a phenomenon that has been studied extensively in social psychology. The brain's decision to help is influenced by the presence of others, with individuals less likely to intervene in an emergency if others are watching. This effect is thought to be due to a diffusion of responsibility, where each person assumes someone else will act. The brain's social cognition system is involved in this decision-making process. The brain's sense of fairness is linked to the anterior insula, a region that processes emotions and bodily sensations. When the brain perceives an unfair situation, the anterior insula becomes active, creating a feeling of disgust or anger. This response is thought to be a fundamental part of human social behavior. The brain's fairness system is essential for maintaining social cohesion. The brain's processing of legal language is often slower and more complex than everyday language, reflecting the specialized nature of legal terminology. Legal texts use precise, technical language that requires careful parsing by the brain. This complexity can make legal documents difficult to understand for non-experts. The brain's language system must work harder to process legal language. The doorway effect, mentioned earlier, can cause people to forget why they entered a room, a phenomenon that has implications for legal testimony. The brain's event boundaries can affect memory, leading to forgetting of information that crosses a physical boundary. This effect can influence how witnesses remember events. The brain's memory system is influenced by the physical environment. The brain can be influenced by authority figures, a phenomenon demonstrated by the Milgram experiment. In this experiment, participants were willing to administer electric shocks to another person when instructed by an authority figure. The brain's response to authority is thought to be influenced by social conditioning and the fear of consequences. This effect shows the power of social influence on behavior. The brain's tendency to conform is called the Asch conformity effect, where individuals change their answers to match the group. In the Asch experiment, participants gave incorrect answers to simple questions when the group gave incorrect answers. The brain's social cognition system is involved in this conformity, as individuals seek to fit in with the group. The brain's response to group pressure is a fundamental aspect of social behavior. The brain's reward system is activated by following rules, creating a feeling of satisfaction when rules are obeyed. This activation is thought to reinforce rule-following behavior. The brain's reward system is essential for maintaining social order. Following rules is often associated with positive feelings. The brain can detect hypocrisy in others, a skill that is essential for social functioning. The brain's theory of mind allows us to infer the mental states of others, including their intentions and beliefs. This ability allows us to detect when someone is being hypocritical. The brain's social cognition system is essential for detecting hypocrisy. The brain's moral reasoning develops over time, with children showing different moral reasoning than adults. The brain's prefrontal cortex, which is involved in moral reasoning, develops throughout adolescence and into early adulthood. This development is associated with more complex moral judgments. The brain's moral system is shaped by experience and development. The brain can feel guilt when breaking a rule, a feeling that is associated with the anterior cingulate cortex. Guilt is a negative emotion that arises when the brain perceives a violation of moral standards. This feeling can motivate behavior change. The brain's guilt system is essential for maintaining social norms. The brain's perception of justice can be influenced by context, with the brain's response to unfairness depending on the situation. The brain's anterior insula is activated by unfairness, but this activation can be modulated by context. This modulation shows that the brain's response to justice is not fixed. The brain's justice system is influenced by social and environmental factors. The brain's capacity for empathy influences adherence to social rules, with more empathetic individuals being more likely to follow rules. The brain's empathy system is mediated by the mirror neuron system and the anterior insula. This system allows us to understand and share the feelings of others. Empathy is essential for social cohesion. The brain's response to punishment is mediated by the amygdala, which processes fear and threat. The brain's fear response is activated by the threat of punishment, motivating rule-following behavior. This response is essential for maintaining social order. The brain's punishment system is a fundamental aspect of social behavior. The brain's response to reward is mediated by the dopamine system, which is activated by positive outcomes. The brain's reward system is activated by following rules, reinforcing rule-following behavior. This reinforcement is essential for maintaining social norms. The brain's reward system is a fundamental aspect of social behavior. The brain's response to social exclusion is similar to physical pain, with the same brain regions being activated. The brain's anterior cingulate cortex and insula are activated by social rejection. This response shows the importance of social connection for the brain. Social exclusion is a powerful motivator for conformity. The brain's response to fairness is influenced by culture, with different cultures having different norms of fairness. The brain's fairness system is shaped by cultural norms and values. This cultural influence shows that the brain's response to fairness is not universal. The brain's fairness system is influenced by social learning. The brain's response to authority is influenced by context, with the brain's response depending on the perceived legitimacy of the authority. The brain's social cognition system evaluates the legitimacy of authority figures. This evaluation influences the brain's response to authority. The brain's authority system is not fixed, but context-dependent. The brain's response to rules is influenced by the perceived fairness of the rules, with unfair rules being less likely to be followed. The brain's fairness system evaluates the fairness of rules. This evaluation influences rule-following behavior. The brain's response to rules is influenced by perceptions of fairness. The brain's response to social norms is influenced by the perceived social consensus, with individuals more likely to follow norms that are widely shared. The brain's social cognition system evaluates social consensus. This evaluation influences norm-following behavior. The brain's response to norms is influenced by social information. The brain's response to rules is influenced by the perceived consequences of breaking the rules, with more severe consequences leading to more compliance. The brain's fear system is activated by the threat of consequences. This activation motivates rule-following behavior. The brain's response to rules is influenced by perceived consequences. The brain's response to rules is influenced by the perceived legitimacy of the rule-makers, with more legitimate authorities being more likely to be obeyed. The brain's social cognition system evaluates legitimacy. This evaluation influences obedience. The brain's response to rules is influenced by the source of the rule. The brain's response to rules is influenced by the perceived consistency of the rules, with inconsistent rules being less likely to be followed. The brain's cognitive system evaluates consistency. This evaluation influences rule-following behavior. The brain's response to rules is influenced by consistency. The brain's response to rules is influenced by the perceived clarity of the rules, with unclear rules being less likely to be followed. The brain's cognitive system evaluates clarity. This evaluation influences rule-following behavior. The brain's response to rules is influenced by clarity. The brain's response to rules is influenced by the perceived relevance of the rules, with irrelevant rules being less likely to be followed. The brain's cognitive system evaluates relevance. This evaluation influences rule-following behavior. The brain's response to rules is influenced by relevance. The brain's response to rules is influenced by the perceived cost of following the rules, with high-cost rules being less likely to be followed. The brain's cost-benefit system evaluates the cost of rule following. This evaluation influences rule-following behavior. The brain's response to rules is influenced by cost. The brain's response to rules is influenced by the perceived benefit of following the rules, with high-benefit rules being more likely to be followed. The brain's reward system evaluates the benefit of rule following. This evaluation influences rule-following behavior. The brain's response to rules is influenced by benefit. The brain's response to rules is influenced by the perceived social pressure to follow the rules, with more social pressure leading to more compliance. The brain's social cognition system evaluates social pressure. This evaluation influences rule-following behavior. The brain's response to rules is influenced by social pressure. The brain's response to rules is influenced by the perceived personal responsibility to follow the rules, with more responsibility leading to more compliance. The brain's executive function system evaluates personal responsibility. This evaluation influences rule-following behavior. The brain's response to rules is influenced by personal responsibility. The brain's response to rules is influenced by the perceived moral obligation to follow the rules, with stronger moral obligation leading to more compliance. The brain's moral reasoning system evaluates moral obligation. This evaluation influences rule-following behavior. The brain's response to rules is influenced by moral obligation. The brain's response to rules is influenced by the perceived emotional connection to the rules, with stronger emotional connection leading to more compliance. The brain's limbic system evaluates emotional connection. This evaluation influences rule-following behavior. The brain's response to rules is influenced by emotional connection. The brain's response to rules is influenced by the perceived personal identity, with individuals more likely to follow rules that align with their identity. The brain's self-system evaluates personal identity. This evaluation influences rule-following behavior. The brain's response to rules is influenced by identity. The brain's response to rules is influenced by the perceived social identity, with individuals more likely to follow rules that align with their social group. The brain's social identity system evaluates group norms. This evaluation influences rule-following behavior. The brain's response to rules is influenced by social identity. The brain's response to rules is influenced by the perceived cultural norms, with individuals more likely to follow rules that align with their culture. The brain's cultural system evaluates cultural norms. This evaluation influences rule-following behavior. The brain's response to rules is influenced by culture. The brain's response to rules is influenced by the perceived historical context, with individuals more likely to follow rules that are historically consistent. The brain's memory system evaluates historical context. This evaluation influences rule-following behavior. The brain's response to rules is influenced by history. The brain's response to rules is a complex process that involves multiple brain systems. The brain integrates information from social, emotional, and cognitive systems to guide rule-following behavior. This integration is essential for maintaining social order. The brain's response to rules is a fundamental aspect of human social behavior. The first known brain surgery, called trepanation, dates back to around 7,000 years ago, with evidence found in Neolithic skulls. Ancient practitioners drilled or scraped holes into the skull, likely to treat head injuries or relieve pressure. Some individuals survived the procedure, as evidenced by healed bone growth around the holes. This early surgery demonstrates that humans have been interested in the brain for millennia. The only organ in the body that does not feel pain is the brain itself, as it lacks nociceptors, the pain-detecting nerve endings. This is why neurosurgeons can operate on the brain while the patient is awake. The surrounding membranes and scalp do have pain receptors, but the brain tissue itself remains insensitive to direct stimulation. This unique property makes brain surgery possible without general anesthesia in some cases. The first fMRI scan of the brain was performed in the early 1990s using a technique that measures blood flow changes related to neural activity. This technology, called functional magnetic resonance imaging, allowed researchers to see which areas of the brain were active during different tasks. fMRI has become a standard tool in neuroscience research, revolutionizing the study of brain function. The first scans were crude by modern standards, but opened up new possibilities for brain research. The largest human brain on record weighed about 5 pounds, or 2.3 kilograms, significantly larger than the average 3-pound brain. This exceptionally large brain belonged to a man with hydrocephalus, a condition that caused fluid buildup in the skull. Despite its size, the brain did not indicate superior intelligence. The record demonstrates the range of normal human brain variation. The first person to win a Nobel Prize for brain research was Camillo Golgi in 1906, who shared the prize with Santiago Ramon y Cajal. Golgi developed a staining technique that allowed visualization of individual neurons, a breakthrough that made modern neuroscience possible. His method, called the Golgi stain, revealed the intricate branching structure of neurons. This discovery was essential for establishing the neuron doctrine. The longest study on memory is the Harvard Grant Study, which began in 1938 and is still ongoing, tracking the lives of a group of men for over 80 years. The study has followed these individuals from young adulthood into old age, collecting data on their physical and mental health. The study has provided valuable insights into the factors that contribute to healthy aging and memory retention. It is one of the longest-running longitudinal studies in history. The first brain bank was established in the 1950s at the University of California, Los Angeles, to collect and store brain tissue for research. Brain banks are essential for studying neurological diseases, providing tissue for researchers to examine. These facilities have been instrumental in advancing understanding of conditions like Alzheimer's and Parkinson's. The first brain bank was a pioneering effort in neuroscience research. The only animal with a brain that never sleeps is a subject of debate, but some researchers have suggested that certain insects, like ants, may never experience sleep in the mammalian sense. Ants have periods of inactivity, but their brain activity does not show the same patterns as mammalian sleep. This question remains unresolved, as sleep is difficult to define across species. The study of sleep in insects is an active area of research. The first EEG recording from a human was made in 1924 by Hans Berger, a German psychiatrist who was fascinated by the brain's electrical activity. His initial recordings were primitive, showing only crude wave patterns, but they proved that brain activity could be measured from the scalp. Berger's work laid the foundation for all subsequent brainwave research. The EEG remains a standard tool in neurology and sleep research. The fastest recorded reaction time is about 100 milliseconds, achieved by elite athletes and individuals with exceptional reflexes. This incredibly fast response is the result of years of training and genetic factors. The brain must process a stimulus and initiate a response in a fraction of a second. Reaction times of this speed are rare and require exceptional neural processing. The only mammal that cannot turn its head is the sloth, which has extra vertebrae in its neck, limiting its range of motion. This anatomical limitation affects the brain's motor coordination, as the sloth must turn its entire body to change its view. The sloth's limited neck mobility is compensated by its ability to rotate its body. This adaptation reflects the sloth's unique evolutionary history. The first successful brain transplant was performed on a dog in the 1950s by Russian surgeon Vladimir Demikhov. Demikhov transplanted a second head onto a dog, creating a two-headed canine that survived for several days. The procedure was not a true brain transplant, as the second head retained its own brain. This experiment demonstrated the technical feasibility of head transplantation, but raised significant ethical questions. The first blood transfusion was performed using animal blood in the 17th century, with early physicians believing that animal blood could cure various ailments. These early transfusions were almost always fatal, as the immune system rejected the foreign blood. The successful transfusion of human blood did not occur until the early 19th century, after the discovery of blood types. This history shows the slow progress of medical knowledge. The existence of neurons as distinct cells was not established until the late 19th century, largely through the work of Santiago Ramón y Cajal. Using a staining technique developed by Camillo Golgi, Cajal was able to visualize individual nerve cells and their intricate branching patterns. This discovery fundamentally changed the understanding of the nervous system as a network of discrete cells. Cajal's work is considered the foundation of modern neuroscience. The first scientific study of memory was conducted by Hermann Ebbinghaus in the 1880s, who used himself as a test subject. Ebbinghaus memorized nonsense syllables and measured how long he retained them, establishing many of the fundamental principles of memory research. His work showed that memory declines rapidly over time, a phenomenon called the forgetting curve. Ebbinghaus's methods are still used in memory research today. The concept of neuroplasticity, the idea that the brain can change and reorganize itself, was not widely accepted until the 1960s and 70s. Early researchers believed that the adult brain was fixed and could not change. The discovery of neuroplasticity has had a profound impact on rehabilitation and treatment of brain injury. This understanding has changed how we think about the brain's potential for recovery. The first known description of the brain's structure was provided by the ancient Greek physician Galen, who believed that the brain was the seat of sensation and thought. While many of his theories were later disproven, his work was influential for centuries. Galen's descriptions of the brain were based on animal dissections, as human dissection was not allowed. His work shaped medical thinking for over 1,000 years. The first theory of memory proposed that memories were stored as physical impressions in the brain, a theory that was proposed by Plato. This theory was influential for centuries, suggesting that memories were like impressions made in wax. It was not until the 19th century that a more sophisticated understanding of memory emerged. Plato's theory reflected the limited knowledge of the time. The first detailed map of the brain's functions was created by phrenologists in the 19th century, who believed that different mental faculties were localized in specific brain regions. While phrenology was ultimately discredited, it contributed to the understanding of brain localization. The idea that different brain regions have different functions is a cornerstone of modern neuroscience. Phrenology was a precursor to modern neuropsychology. The first neurotransmitter to be discovered was acetylcholine, which plays a role in muscle contraction and memory. This discovery was a major breakthrough in understanding how the brain communicates. Acetylcholine was identified in the early 20th century, opening up new avenues of research. Neurotransmitters are essential for brain function. The first recordings of brain activity were made using electrodes placed on the scalp, called electroencephalograms or EEGs. This technique was first used in the 1920s and is still used today to diagnose sleep disorders and other conditions. EEGs measure the electrical activity of the brain, providing a window into brain function. The EEG is one of the oldest and most widely used tools in neuroscience. The first successful brain stimulation experiments were conducted in the 1950s by Wilder Penfield, who stimulated the brains of awake patients during surgery. Penfield's work mapped the motor and sensory cortex, creating the homunculus. These experiments showed that different parts of the brain control different functions. Penfield's work was essential for understanding brain organization. The first use of brain imaging to study cognition occurred in the 1980s, using positron emission tomography, or PET scans. PET scans measure blood flow in the brain, indicating which areas are active. This technology was later replaced by fMRI, which provides better spatial and temporal resolution. Brain imaging has revolutionized the study of cognition. The first study of the brain's reward system was conducted in the 1950s, using electrical stimulation of the brain in rats. Rats would press a lever to stimulate certain brain regions, suggesting that these areas were associated with pleasure. This research identified the brain's reward pathways. The reward system is now known to involve dopamine. The first study of the brain's fear system was conducted in the 1930s, using electrical stimulation of the amygdala in animals. Stimulation of the amygdala caused fear responses, suggesting that this region is involved in fear processing. This research laid the foundation for understanding the brain's emotional systems. The amygdala is now known to be central to fear. The first study of the brain's memory system was conducted in the 1950s, using patients with hippocampal damage. These patients, including the famous patient HM, were unable to form new memories. This research showed that the hippocampus is essential for memory formation. HM's case was a landmark in memory research. The first study of the brain's language system was conducted in the 19th century, using patients with brain damage. These studies identified Broca's and Wernicke's areas, which are involved in language production and comprehension. This research showed that language is localized in specific brain regions. These studies were essential for understanding the brain's organization. The first study of the brain's visual system was conducted in the 1950s, using electrodes to record from the visual cortex of animals. These studies identified the organization of the visual cortex, showing that it is organized into columns. This research was essential for understanding how the brain processes visual information. The visual cortex is one of the most studied areas of the brain. The first study of the brain's motor system was conducted in the 1950s, using electrical stimulation of the motor cortex in animals. These studies showed that different parts of the motor cortex control different body parts. This research was essential for understanding motor control. The motor cortex is essential for voluntary movement. The first study of the brain's sleep system was conducted in the 1950s, using EEG recordings to study sleep patterns. These studies identified REM sleep and its association with dreaming. This research showed that sleep is an active process. The study of sleep has advanced significantly since these early studies. The first study of the brain's attention system was conducted in the 1950s, using behavioral experiments to study attention. These studies identified the limits of attention, showing that attention is a limited resource. This research was essential for understanding cognitive processing. Attention is now known to involve multiple brain regions. The first study of the brain's consciousness was conducted in the 19th century, with early philosophers and scientists speculating about the nature of consciousness. The scientific study of consciousness began in the 20th century with the development of brain imaging. Consciousness remains one of the most challenging topics in neuroscience. The study of consciousness is ongoing. The first study of the brain's development was conducted in the 20th century, using animal models to study brain growth. These studies showed that the brain develops through a combination of genetic and environmental factors. This research was essential for understanding brain development. Brain development is a complex and ongoing process. The first study of the brain's aging was conducted in the 20th century, using longitudinal studies to track cognitive changes over time. These studies showed that cognitive decline is not inevitable, but can be influenced by lifestyle factors. This research was essential for understanding healthy aging. The study of brain aging is an active area of research. The first study of the brain's plasticity was conducted in the 20th century, showing that the brain can change in response to experience. This research revolutionized the understanding of the brain's potential for recovery. Neuroplasticity is now a central concept in neuroscience. The study of plasticity is ongoing. The brain combines signals from multiple senses to create a unified perception, a process called multisensory integration. The brain does not process sensory information in isolation, but integrates visual, auditory, tactile, and other signals into a coherent experience. This integration occurs in the superior colliculus and other brain regions. The brain's ability to combine sensory information is essential for understanding the world. Synesthesia is a condition where one sense triggers another, such as seeing colors when hearing sounds. In synesthesia, the brain's sensory pathways are cross-wired, leading to unusual perceptual experiences. This condition is thought to be caused by increased connectivity between sensory regions. Synesthesia is a fascinating example of the brain's variability. The brain can perceive odors that are undetectable consciously, with the olfactory system processing information below the level of awareness. The brain's olfactory system is directly connected to the limbic system, which processes emotion and memory. This direct connection allows smells to influence mood and behavior without conscious awareness. The brain's olfactory system is one of the most primitive sensory systems. The brain's visual system processes color, motion, and shape separately, in parallel pathways. The visual cortex contains specialized areas for processing different aspects of visual information. The what pathway processes object identity, while the where pathway processes spatial location. This parallel processing allows the brain to efficiently handle complex visual information. The brain has a specific area for processing faces, called the fusiform face area, which is located in the temporal lobe. This area responds selectively to faces, showing greater activation when viewing faces than other objects. Damage to this area can cause prosopagnosia, the inability to recognize faces. The fusiform face area is essential for social interaction. The brain can localize sound to within a few degrees of accuracy, using tiny differences in the time and intensity of sound arriving at each ear. The brain's auditory system calculates these differences to determine the direction of the sound source. This process is so precise that humans can detect sound location changes of less than 1 degree. The brain's auditory localization is essential for survival. The brain can filter out background noise to focus on a single speaker, a process called the cocktail party effect. The brain's auditory system can selectively attend to one sound stream while ignoring others. This ability is mediated by the auditory cortex and the prefrontal cortex. The cocktail party effect is essential for communication in noisy environments. The brain's sense of touch is more sensitive on the fingertips, which have a high density of tactile receptors. The brain's somatosensory cortex has a disproportionate representation of the fingertips, reflecting their importance for exploration. This enhanced sensitivity allows for fine discrimination of texture and shape. The fingertips are essential for interacting with the world. The brain can perceive phantom tastes, where taste is experienced without any actual stimulus. This phenomenon is thought to be caused by the brain's gustatory system being activated spontaneously. Phantom tastes can occur after damage to the gustatory cortex. The brain's taste system is complex and not fully understood. The brain's perception of time can be distorted by emotions, with time seeming to pass more slowly during frightening or exciting events. The brain's time perception is influenced by the amygdala, which processes emotion. This distortion is thought to be due to increased arousal and attention. The brain's perception of time is not constant, but depends on context. The brain uses magnocellular and parvocellular pathways for vision, which process different aspects of visual information. The magnocellular pathway processes motion and spatial information, while the parvocellular pathway processes color and fine detail. These pathways are parallel and operate independently. The brain's visual system is highly specialized. The brain can integrate sensory information from different sides of the body, creating a unified perception of the body. The brain's somatosensory cortex integrates information from both sides of the body. This integration is essential for maintaining a coherent sense of the body. The brain's body representation is not split but unified. The brain's visual system can compensate for the blind spot, where the optic nerve exits the retina. The brain fills in the missing information, creating a seamless visual field. This filling-in process occurs automatically and without conscious awareness. The brain's visual system is constantly constructing a complete representation of the world. The brain's auditory system can process the pitch, timbre, and location of sounds simultaneously. The brain's auditory cortex has specialized areas for processing different aspects of sound. This parallel processing allows for efficient sound analysis. The brain's auditory system is essential for communication. The brain's somatosensory system processes touch, temperature, and pain, with different receptors for each modality. The brain's somatosensory cortex has different areas for processing different types of tactile information. This specialization allows for precise perception of the body's interaction with the environment. The brain's somatosensory system is essential for survival. The brain's olfactory system is unique in its direct connection to memory and emotion, bypassing the thalamus. This direct connection is why smells can evoke such vivid memories. The brain's olfactory system is essential for detecting food and danger. The sense of smell is closely linked to emotional processing. The brain's gustatory system processes taste, with different receptors for sweet, sour, salty, bitter, and umami. The brain's gustatory cortex integrates taste information with other sensory inputs. This integration creates the perception of flavor. The brain's taste system is essential for food selection. The brain's vestibular system processes balance and head position, providing information about movement and orientation. The brain's vestibular system is located in the inner ear and is essential for maintaining posture. This system integrates with visual and proprioceptive information. The brain's vestibular system is essential for movement. The brain's proprioceptive system processes information about body position, providing feedback about the body's location in space. The brain's proprioceptive system is mediated by receptors in the muscles and joints. This system is essential for coordinated movement. The brain's proprioceptive system operates without conscious awareness. The brain's interoceptive system processes information about the body's internal state, including heart rate, hunger, and thirst. The brain's interoceptive system is mediated by the insula, which processes internal bodily sensations. This system is essential for maintaining homeostasis. The brain's interoceptive system is often associated with emotional awareness. The brain's nociceptive system processes pain, with different pathways for fast and slow pain. The brain's nociceptive system is mediated by the thalamus and the somatosensory cortex. This system is essential for detecting tissue damage. The brain's pain system is complex and involves multiple brain regions. The brain's thermoreceptive system processes temperature, with different receptors for warmth and cold. The brain's thermoreceptive system is mediated by the hypothalamus, which regulates body temperature. This system is essential for maintaining a stable internal environment. The brain's thermoreceptive system is closely linked to the autonomic nervous system. The brain's visual system can process information from the periphery of the visual field, detecting movement and changes in light. The brain's visual system is sensitive to peripheral vision, which is essential for detecting threats. The periphery of the visual field is processed differently than the center. The brain's visual system is adapted for survival. The brain's auditory system can detect the direction of sound, using the head as a sound shadowing device. The brain's auditory system compares the intensity of sound at each ear to determine location. This process is essential for localizing sounds in the environment. The brain's auditory system is highly specialized for spatial processing. The brain's somatosensory system can detect the texture of objects, using information from the fingertips. The brain's somatosensory system processes texture information through specialized receptors. This information is integrated with other sensory inputs. The brain's somatosensory system is essential for tactile exploration. The brain's olfactory system can detect thousands of different odors using a large family of olfactory receptors. The brain's olfactory system is highly sensitive to odor molecules. This sensitivity is essential for detecting food and danger. The brain's olfactory system is one of the most complex sensory systems. The brain's gustatory system can detect the intensity of taste, using receptors that respond to different concentrations. The brain's gustatory system is sensitive to the intensity of taste stimuli. This sensitivity is essential for detecting the quality of food. The brain's taste system is closely linked to the reward system. The brain's vestibular system can detect acceleration and deceleration, providing information about movement. The brain's vestibular system is sensitive to changes in motion. This sensitivity is essential for maintaining balance. The brain's vestibular system is closely linked to the visual system. The brain's proprioceptive system can detect the position of the body in space, using information from muscles and joints. The brain's proprioceptive system is essential for coordinated movement. This system operates without conscious awareness. The brain's proprioceptive system is essential for motor control. The brain's interoceptive system can detect changes in heart rate, providing information about the body's state. The brain's interoceptive system is essential for emotional awareness. This system is closely linked to the limbic system. The brain's interoceptive system is essential for understanding the body's needs. The brain's nociceptive system can detect the location of pain, providing information about the source of injury. The brain's nociceptive system is essential for survival. This system is closely linked to the motor system. The brain's pain system is complex and involves multiple brain regions. The brain's thermoreceptive system can detect changes in temperature, providing information about the environment. The brain's thermoreceptive system is essential for maintaining body temperature. This system is closely linked to the hypothalamus. The brain's thermoreceptive system is essential for survival. The brain's sensory systems are constantly processing information from the environment, integrating signals from multiple modalities. The brain's sensory systems are essential for perception and action. This integration is a fundamental feature of brain function. The brain's sensory systems are highly specialized and complex. The brain's perception of the world is not a direct reflection of reality, but a construction based on sensory input. The brain's perceptual system is constantly interpreting sensory information, making inferences about the world. This construction is essential for understanding the environment. The brain's perception is a product of its neural processing. The brain's sensory systems are essential for survival, providing information about the environment and the body's state. The brain's sensory systems are constantly active, even during sleep. This activity is essential for maintaining awareness. The brain's sensory systems are a fundamental feature of human experience. The brain's limbic system is central to emotional processing, a network of structures that includes the amygdala, hippocampus, and hypothalamus. This system is involved in the generation and regulation of emotions, as well as the formation of emotional memories. The limbic system is often called the emotional brain because of its role in affective processing. Damage to this system can cause significant emotional disturbances. The amygdala is involved in processing fear and threat, responding rapidly to potential dangers in the environment. This almond-shaped structure is located deep in the temporal lobe and is essential for the detection of threat. The amygdala activates the fight-or-flight response when it perceives danger. Its response is fast and automatic, occurring before conscious awareness of the threat. The brain can experience emotional contagion from others, where emotions are transmitted from person to person. The brain's mirror neuron system is involved in this transmission, allowing us to mimic and feel the emotions of others. This contagious effect is essential for social bonding and empathy. Emotional contagion can occur through facial expressions, tone of voice, and body language. The brain's prefrontal cortex helps regulate emotional responses, acting as a brake on the amygdala. This region is involved in the cognitive control of emotion, allowing us to modulate our emotional reactions. The prefrontal cortex is essential for emotional regulation, preventing us from overreacting to emotional stimuli. This regulation is essential for social functioning. The brain releases oxytocin during social bonding, creating feelings of trust and attachment. Oxytocin is a neuropeptide that is released during positive social interactions, such as hugging or bonding with a loved one. This release promotes social connection and reduces feelings of anxiety. Oxytocin is often called the love hormone because of its role in social bonding. The brain can suppress emotional responses consciously, using cognitive strategies to regulate emotions. This conscious suppression involves the prefrontal cortex, which inhibits the amygdala's response. This suppression can be effective in the short term, but may have long-term costs. The brain's ability to regulate emotions is essential for social functioning. The brain's emotional memory is often stronger than neutral memory, with emotional events being more likely to be remembered. The amygdala enhances memory consolidation for emotional events, tagging them as important. This is why you are more likely to remember your wedding day than an ordinary Tuesday. The brain's emotional memory system is essential for survival. The brain can feel social pain, such as rejection, in a similar way to physical pain. The same brain regions are activated by social rejection and physical pain, including the anterior cingulate cortex and the insula. This overlap suggests that social and physical pain share neural mechanisms. Social pain is a powerful motivator for social connection. The brain's mood can be affected by the gut microbiome, which communicates with the brain through the gut-brain axis. The microbiome produces neurotransmitters and other compounds that affect brain function. This communication is mediated by the vagus nerve and the immune system. The gut-brain axis is an area of active research in neuroscience. The brain can have a happiness set point that is partially genetic, with some people being naturally happier than others. This set point is influenced by genetic factors that affect neurotransmitter levels. However, the set point can be influenced by life experiences and intentional practices. Happiness is not entirely determined by genetics. The brain's expression of emotions is culturally influenced, with different cultures having different norms for emotional expression. The brain's emotional system is shaped by cultural learning, with individuals learning to express emotions in culturally appropriate ways. This cultural influence is evident in the different display rules for emotions across cultures. The brain's emotional system is both universal and culturally specific. The brain can be primed by emotional words to respond faster to related words, a phenomenon called emotional priming. The brain's semantic network is organized by emotional content, with related emotional words being closely linked. This priming effect is automatic and occurs without conscious awareness. Emotional priming influences how we process information. The brain's positive emotions are processed by the reward system, which is activated by pleasurable experiences. The brain's reward system involves the release of dopamine, creating feelings of pleasure and motivation. This system is activated by eating, social interaction, and other rewarding experiences. The reward system is essential for reinforcing behavior. The brain's negative emotions are processed by the fear and threat system, which is activated by potential dangers. The brain's fear system involves the amygdala and the hypothalamus, which trigger the stress response. This system is essential for survival, alerting us to potential threats. The fear system is quick and automatic. The brain's emotional regulation can be improved through practice, with mindfulness and cognitive behavioral therapy being effective. The brain's plasticity allows for changes in emotional regulation with practice. Mindfulness practice has been shown to reduce amygdala reactivity and increase prefrontal cortex activity. Emotional regulation is a skill that can be learned. The brain's emotional response is influenced by context, with the same stimulus evoking different emotions in different situations. The brain's emotional system is context-dependent, with the interpretation of a stimulus influencing the emotional response. This context dependence is mediated by the prefrontal cortex. The brain's emotional response is not fixed but flexible. The brain's emotional response is influenced by memory, with past experiences shaping current emotional reactions. The brain's emotional memory system tags past experiences with emotional significance. This tagging influences how we respond to similar situations in the future. Emotional memories are powerful influences on behavior. The brain's emotional response is influenced by attention, with focusing on emotional stimuli increasing the emotional response. The brain's attention system can amplify or dampen emotional responses. This modulation is mediated by the prefrontal cortex. Attention is a powerful regulator of emotion. The brain's emotional response is influenced by expectations, with expectations shaping the emotional experience. The brain's expectation system influences how we interpret emotional stimuli. This influence is mediated by the prefrontal cortex. Expectations can significantly impact emotional experiences. The brain's emotional response is influenced by social context, with the presence of others modulating emotional reactions. The brain's social cognition system influences emotional responses in social situations. This influence is mediated by the prefrontal cortex and the mirror neuron system. Social context is a powerful modulator of emotion. The brain's emotional response is influenced by physiological state, with changes in the body affecting emotions. The brain's interoceptive system monitors the body's state, influencing emotional experience. This is why a racing heart can make you feel anxious. The brain's emotional system is closely linked to the body. The brain's emotional response is influenced by neurotransmitters, which modulate emotional processing. Serotonin is involved in mood regulation, while dopamine is involved in reward and motivation. Imbalances in these neurotransmitters can lead to emotional disorders. The brain's emotional system is regulated by complex neurochemical interactions. The brain's emotional response is influenced by hormones, which affect emotional processing. Cortisol, the stress hormone, can increase emotional reactivity. Oxytocin, the bonding hormone, can reduce anxiety. The brain's emotional system is influenced by the endocrine system. The brain's emotional response is influenced by sleep, with sleep deprivation increasing emotional reactivity. Lack of sleep affects the amygdala, making it more reactive to emotional stimuli. This increased reactivity can lead to mood disturbances. Sleep is essential for emotional regulation. The brain's emotional response is influenced by exercise, which can improve mood and reduce anxiety. Exercise increases the release of endorphins and other mood-enhancing chemicals. This effect is thought to be mediated by the brain's reward system. Regular exercise is beneficial for emotional health. The brain's emotional response is influenced by diet, with certain foods affecting mood. A diet rich in omega-3 fatty acids has been associated with better mood regulation. The brain's emotional system is influenced by nutritional factors. Diet is an important factor in emotional health. The brain's emotional response is influenced by stress, with chronic stress leading to emotional dysregulation. Stress affects the amygdala and the prefrontal cortex, impairing emotional regulation. This dysregulation can lead to anxiety and depression. Managing stress is essential for emotional health. The brain's emotional response is influenced by social support, with supportive relationships buffering against stress. Social support activates the brain's reward system and reduces stress responses. This buffering effect is mediated by oxytocin and other neuropeptides. Social support is essential for emotional resilience. The brain's emotional response is influenced by personality, with different personality traits being associated with different emotional patterns. Neuroticism is associated with increased negative emotionality, while extroversion is associated with increased positive emotionality. The brain's emotional system is influenced by stable individual differences. Personality is a major factor in emotional experience. The brain's emotional response is influenced by genetics, with heritability accounting for a significant portion of emotional variability. Twin studies have shown that genetic factors influence emotional reactivity and regulation. However, environmental factors also play a significant role. The brain's emotional system is influenced by both genes and environment. The brain's emotional response is influenced by development, with emotional processing changing over the lifespan. Children show different emotional patterns than adults, reflecting the maturation of the brain. The prefrontal cortex, which regulates emotions, develops throughout adolescence. Emotional development is a lifelong process. The brain's emotional response is influenced by culture, with different cultures having different norms for emotional expression. Culture shapes the brain's emotional system through social learning. This cultural influence is evident in the different display rules for emotions. The brain's emotional system is both universal and culturally specific. The brain's emotional response is influenced by learning, with emotional associations being formed through experience. The brain's emotional system can learn new associations, linking neutral stimuli to emotional responses. This learning is mediated by the amygdala and the hippocampus. Emotional learning is a fundamental aspect of brain function. The brain's emotional response is a complex process that involves multiple brain systems. The brain integrates information from the limbic system, the prefrontal cortex, and the autonomic nervous system to generate emotional experiences. This integration is essential for adaptive behavior. The brain's emotional system is a fundamental aspect of human experience. The brain uses more energy than any other organ in the body, consuming about 20% of the body's total energy, despite being only 2% of total body weight. This high energy consumption is necessary for maintaining neural activity, with the brain constantly processing information even during sleep. The brain's energy demands are so high that even brief interruptions in blood flow can cause significant damage. This energy consumption is a reflection of the brain's constant activity. The brain's gray matter is actually pinkish in living tissue, not the gray color seen in preserved specimens or diagrams. The gray color appears only after death, when the blood drains from the tissue and the brain is fixed in preservatives. In life, the brain's gray matter has a pinkish hue due to the high density of blood vessels supplying oxygen and nutrients. The color difference is a reminder that preserved specimens do not represent living tissue. The brain is mostly fat, about 60% of its dry weight, which is essential for its structure and function. This high fat content is necessary for the formation of cell membranes and the myelin sheath that insulates nerve fibers. The brain's lipid composition is unique, with specific types of fats required for proper neural function. A diet lacking in essential fatty acids can affect brain health. The brain does not store memories like a filing cabinet, with each memory stored in a specific location. Instead, memories are distributed across the cortex, with different aspects of a memory stored in different regions. The visual aspects of a memory are stored in the visual cortex, the sounds in the auditory cortex, and the emotions in the limbic system. The brain reconstructs memories from these distributed components. The brain can process the concept of zero, an abstract concept that is surprisingly rare in the animal kingdom. Recognizing zero as a quantity, rather than just the absence of something, requires abstract thinking. The brain's ability to process zero is associated with the parietal cortex, which handles numerical processing. This ability develops relatively early in human development. The brain's left hemisphere tends to process language more than the right hemisphere, with the left being dominant for most people. This specialization is called lateralization and is present from early childhood. About 95% of right-handed people have language centers in the left hemisphere. Even in left-handed people, the majority have left hemisphere language dominance. The brain can recover from some injuries through neuroplasticity, the brain's ability to reorganize and form new connections. This recovery is not guaranteed, but is more likely in younger individuals and those with less severe injuries. The brain's plasticity allows for compensation, where other regions take over functions of damaged areas. This recovery is a remarkable feature of the brain. The brain contains about 400 miles of blood vessels, an intricate network that ensures every neuron is within a tiny distance of a capillary. This vascular system is essential for supplying oxygen and nutrients to the brain's high-demand tissues. The brain's blood vessels are highly branched, creating a dense network. This network is essential for brain function. The brain's optic nerve is connected directly to the eye, carrying visual information from the retina to the visual cortex. This direct connection is why a blow to the back of the head can cause visual disturbances. The optic nerve is actually an extension of the brain itself, not a separate peripheral nerve. This direct connection is essential for visual processing. The brain's motor cortex helps coordinate fine movements, with different areas controlling different body parts. The motor cortex is located in the frontal lobe, just in front of the central sulcus. This region is essential for voluntary movement, planning, and executing motor actions. Damage to the motor cortex can cause paralysis. The brain's sensory cortex processes touch, temperature, and pain, with different areas responding to different body parts. The sensory cortex is located in the parietal lobe, just behind the central sulcus. This region is essential for tactile perception, processing information from the body's surface. The sensory cortex is organized somatotopically, with adjacent body parts represented adjacently. The brain is not fully developed until the mid-20s, with the prefrontal cortex being one of the last regions to mature. This late development is associated with the maturation of higher cognitive functions, including impulse control and decision-making. The prefrontal cortex is essential for complex planning and social behavior. This late development explains some of the behavioral differences between adolescents and adults. The brain's default mode network is active when you are not focused on an external task, engaging in internally directed thought. This network involves the medial prefrontal cortex, posterior cingulate cortex, and other regions. The default mode network is associated with daydreaming, self-reflection, and mind-wandering. Its activity is reduced during focused attention. The brain's hippocampus is essential for spatial navigation, with place cells firing in response to specific locations. The hippocampus is also essential for memory formation, with new memories being consolidated there. This dual function makes the hippocampus essential for both navigation and memory. Damage to the hippocampus can impair both functions. The brain's cerebellum is involved in motor coordination and balance, with more neurons than the rest of the brain combined. The cerebellum is essential for fine motor control, coordinating complex movements. Damage to the cerebellum can cause ataxia, a loss of coordination. The cerebellum is also involved in some cognitive functions. The brain's brainstem is responsible for basic life support functions, including breathing and heart rate. The brainstem is essential for survival, with damage often being catastrophic. This region is one of the most evolutionarily ancient parts of the brain. The brainstem is essential for maintaining life. The brain's hypothalamus regulates body temperature and other homeostatic functions, acting as the body's thermostat. The hypothalamus is essential for maintaining a stable internal environment. Damage to the hypothalamus can cause significant disruptions in body function. The hypothalamus is a small but powerful region. The brain's pituitary gland controls growth and other endocrine functions, acting as the master gland. The pituitary is essential for regulating hormone release, influencing growth, metabolism, and reproduction. This gland is controlled by the hypothalamus. The pituitary is essential for endocrine function. The brain's pineal gland produces melatonin, regulating the sleep-wake cycle. The pineal is essential for circadian rhythm regulation, with melatonin production increasing in darkness. This gland is sometimes called the third eye because of its sensitivity to light. The pineal is essential for sleep regulation. The brain's amygdala is involved in processing fear and threat, with rapid responses to potential dangers. The amygdala is essential for survival, alerting us to potential threats. This region is quick and automatic, responding before conscious awareness. The amygdala is essential for emotional processing. The brain's reward system is involved in motivation and pleasure, releasing dopamine in response to rewarding experiences. The reward system is essential for reinforcing behavior, encouraging us to repeat rewarding actions. This system is activated by food, social interaction, and other rewards. The reward system is essential for learning. The brain's language system is lateralized to the left hemisphere for most people, with Broca's and Wernicke's areas being essential. These regions are essential for language production and comprehension. Damage to these areas can cause aphasia, a language impairment. The language system is a uniquely human feature. The brain's visual system is one of the most studied areas of the brain, with extensive knowledge about its organization. The visual system is essential for perception, processing information from the eyes. This system is organized into specialized pathways for color, motion, and form. The visual system is a model for understanding brain function. The brain's auditory system processes sound with specialized areas for pitch, timbre, and location. The auditory system is essential for communication, processing speech and other sounds. This system is highly specialized, with different regions for different aspects of sound. The auditory system is essential for social interaction. The brain's somatosensory system processes touch, temperature, and pain, with different receptors for each modality. The somatosensory system is essential for interacting with the environment, providing feedback about the body's surface. This system is highly sensitive, allowing for fine discrimination. The somatosensory system is essential for survival. The brain's olfactory system is unique in its direct connection to memory and emotion, bypassing the thalamus. The olfactory system is essential for detecting food and danger, with smells evoking strong memories. This system is highly sensitive, detecting thousands of different odors. The olfactory system is essential for survival. The brain's gustatory system processes taste, with receptors for sweet, sour, salty, bitter, and umami. The gustatory system is essential for food selection, detecting the quality of food. This system is closely linked to the reward system, with tasty foods being rewarding. The gustatory system is essential for survival. The brain's vestibular system processes balance and head position, providing information about movement and orientation. The vestibular system is essential for maintaining posture, integrating with visual and proprioceptive information. This system is highly sensitive, detecting changes in motion. The vestibular system is essential for movement. By now, you have likely forgotten the first fact from this collection. That is the intended effect. Sleep is not a failure of attention, but a successful transition. As you drift further, consider this. The brain does not stop working while sleeping. It simply reorganizes. And now, it is time to let it do its quiet work. One last small quiet fact before you go. The brain produces about 50,000 thoughts per day on average, though most of them are not particularly important. They are like clouds passing through the mind, forming and dissolving without leaving a trace. This is one of them, and it is already beginning to fade. The brain is the only organ in the body that cannot feel pain, yet it is the source of all pain you have ever felt. It can simulate the feeling of a broken heart and the warmth of a summer day without ever leaving the darkness of your skull. It is a closed box that contains an entire universe, and right now, it is settling into the slow, rhythmic patterns of deep rest. The neurons that have been firing to process these words are beginning to fire more slowly and more synchronously. The electrical activity that powered your attention is shifting into the long, slow waves of stage 3 sleep. This is the brain's way of saying that it is finished with input for the night. It is ready to begin its own quiet internal work. There is no more information coming, no more facts to process, no more words to understand. Just the soft sound of your own breathing and the gentle stillness of a mind that has finally stopped reaching for the next thing. Everything you have heard tonight is still there, somewhere in the distributed network of your memory. But it does not need to be found right now. Sleep is not the end of thought. It is the beginning of the brain's own private processing, a time when it sorts, files, and strengthens the connections that matter. You do not need to do anything. The brain will take care of it. And in the morning, you will not remember this last fact. And that is exactly how it should be. Good night.